Hey guys, can you see me now? What's the crack? How are we doing? Hey guys, can you see me now? What's the crack? How are we doing? Hey guys, can you see me now? Sorry, I forgot to mute YouTube. Sorry about the repeat there. How are we doing? Last exam for most of you, right? GCSEs are nearly done. One more to go. Hey Kai, hey Sarah, hey Gwen, hey Eminence. How are we doing? Hey Rifki, thank you for your help. Isn't this the person in the thumbnail? What do you mean? I don't look the same. My hair's up. Hey Happy, hey James. 2 exams tomorrow. What's the 2 exams tomorrow? Physics and what? 2 exams tomorrow is a bit mad, no? That's hardly fair. Like 2 exams tomorrow is actually mad. Hey Ash, what's the crack? 2 exams is so good because the weather is so good this week as well. So you're going to do your 2 exams and then it's going to be blissful week of sun and like you'll have such a long summer. So yeah, just keep the focus. Further maths is tomorrow as well, Yusuf. Spanish and further maths, some of you. Yep, they're coming in quick. Anyone here wasn't here for the first cram, new to the second cram? I heard that basically we really liked that first paper, eh? New, Zina, you're new. Mohammed, yes, all the sciences. That's the way to go. That's what I did. I did all the sciences. Paper 1 was nice. Nimra. Paper 1 was lovely, Evie. This is good. Paper 1 was so good. Paper 1 was great. I love this. British, yes, we're going to begin. My dog, I don't even hear him, but he's going mad right now. He's got his ball beneath the couch. Okay, so guys, why should we even listen to me? And hopefully you guys know me from the first cram, but I have been a physics teacher for a few good years now. And when I did your GCSEs, I got 70 stars and 4 A's. And then I did physics, math, biology, and chemistry for my A-levels and got 4 A stars. So hopefully you guys might join us from our A-level physics course. So you might be like, what are we even doing today? So this is an overview of what we're doing today. So you can not ask me all the time for what times things are at. So hopefully if you're new and you see that everyone's typing the chat and you can't get access to chat, you should see on the chat it says subscribers only. So you just need to go across and hit subscribe and then you can type in the chat as well. So when we have questions, we go for it. So yeah, I see a few questions as well asking, are we doing triple and combined science? Like I've said over here, is the same in all topics apart from a few extra topics, right? But the main content is the same. So all of it is useful for combined and triple, but please remember we're aiming this at a higher tier, right? It's not aimed at foundation tier, it's aimed at a higher tier. And the last little bit will be triple only, so some type of induced potential difference and space physics. Helene, it's aimed all at AQA, but like 90% of it is the same for Edexcel and for OCR. Yeah. They are like triples, mainly space physics, but there's like a little bit of extra content like moments and stuff. Yeah, blessing, sorry, it's all aimed at a higher tier. Some of it is useful for foundation tier, but it's aimed at higher tier. Yeah. So if you don't have your formula sheets, you can just scan the QR code here and you get access to them. That's combined and triple. And yes, and I'll try to point them out, just remind me to do that. And what we're going to start with is forces, then we're going to do waves, we're going to do magnetism and electromagnetism, and then we're going to start that triple stuff. So it's mainly going to be space physics, but there'll also be some moments and there'll be some induced physics. Okay, so just one other thing I want to point out in case some of you are on that foundation and when we're doing those higher questions, you want to know what to do. Something here that you could find useful is my TikTok page. So the TikTok page, you can see that there's loads of categories, right? So let's, for example, you want to score across to the category of, I don't know, you're really struggling with forces. You click on forces and then you can see that I've got all these like different questions for you. You just like click through the forces. So this is quite good for you guys to look at maybe like the day before your exam. So tomorrow morning, that might be quite good for something to look through. Okay, so just like loads of extra stuff there for you for that extra vision. Erin, yes, there's a workbook. The workbook is in the description. So if you go down to the description there, the workbook link is there. Yeah. Okay, Riley, yes, beautiful, getting started, beautiful. The first question then is what is 5 kilonewtons? So yes, this is for technically foundation tier can do this as well. So 5 kilonewtons, someone said if they gave me 1k of cash, hopefully I would get 1,000 pounds. So 5 kilonewtons. Yeah, beautiful, everybody. Easy, easy, easy. Good job. It's going to be 5,000 then, and it's capital N. I saw a few people in there put a little n. Okay, triple physicists especially should know what a little n is, but combined should also know what a little n is. What does that little n stand for? So it doesn't stand for Newton. Yeah, Irish, thank you. It stands for nano, right? It stands for nano. Let's see the workbook just there if you want it to make notes in. It'd probably be helpful to follow the questions a lot. And what does nano stand for? Nanometer, nanoparticles. Yeah, what size is it nano? Yeah, Bella, beautiful. It's times 10 to the power of -9. Okay, so that's something that triple for sure has to know, but combined just needs to make sure that they're aware of it now. Okay, so yeah, 5 kilonewtons is 5,000 newtons. Good. What about 2 centimeters? If we had to put that into meters, what we do? Yeah, Fuzan, it's aimed at AQA, but again, like 90% is the same as it for at Excel and OCR. I'm seeing a lot of 0.02 meters, which is beautiful. Good. So the way I remember it is like history. You have a century. A century is 100 years. So there's 100 centimeters inside 1 meter. So we want to get out of centimeter. What we do is that we divide by 100. Okay, so that's why we divide by 100, and we can figure out what that is then in meters. Good. Cooper, yes. Okay, what about millimeters to meters? How would you do that? How would you get millimeters into meters? I'm seeing a lot of 0.6. 0.6 is 0.6. Yeah, beautiful, good. 0.6 is going to be 0.6 meters. Up to you how to remember it, but I mean a millipede's like an insect. I don't know if you've ever seen it. So an insect is a millipede. It's got 1,000 legs. So it kind of looks like a worm, but it has like 1,000 legs on it. It's called a millipede. So millipede's got 1,000 legs. There's 1,000 millimeters inside 1 meter. So we want to get out of that milli. The math we do there is that we have to divide by 1,000. So that's why we had divide by 1,000 to get out of that millimeters. Yeah, nice. Okay, next one. If I've got 20 milliamps, this one is quite common and it throws a lot of people. Yeah, beautiful, good. That's going to be my 0.02 amps. Yeah, Emma, perfect. ZY, perfect. Good. Yeah, nice. Good. So again, what we do to get out of that milli is divide by 1,000. To get out of the milli, what we're going to do is divide by 1,000. Nice. Okay, again, triple should be pros this, but combined need to know it. This would only be a higher tier question. So which is larger, 12GN or 900MN? What does it even mean? 12GN or 900MN? Purple, just be careful how you write it. Okay, perfect. Like everybody's saying the giga. Good. Thank you for saying giga, duck. So yeah, 12GN is the bigger one. What does G stand for? Yeah, good praises. Giga is always bigger than mega. Good. What is giga? Yeah, Bella, perfect. Yeah, good. Right, 12 giganewtons. Yeah, PN, good job. 12 giganewtons is 12 times 10 to the power of 9, right? You take the number 12 and you move it 9 places bigger. But if it was 900 meganewtons, mega, yeah, Matthew, mega is like megabucks or like million. So that's 900 million, 900 times 10 to the power of 6. Good. So if I had 12 times power 9, we move it 9 places bigger. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 1, 2, 0, 0, 0, 0, 0, 0, 0, 0, 0. And 900 times power 6 means you move 900 and you take it 6 places better. So this is that many zeros. So you can clearly see this number is much bigger than this number. Good. Yeah, good, good, good. No, Musab, no, don't. Okay, please make sure you're very aware to do these because you're going to have unit conversions the whole way through the paper. Okay, the whole way through the paper, and you'll always get 1 mark for remembering about those unit conversions. So don't lose that 1 mark the whole way through the paper, right? Okay, so let's keep the focus on our units. Okay. So hopefully we're excited to get cracking into the harder stuff. I see 108 of you already are excited to get started. So if you're happy to be here, it's free. Please hit the like button. And remember, if you want to type in the chat, you just need to be a subscriber. So you just need to hit that subscribe button and then you can type in the chat and I can see your answers and your questions. Yeah. Okay. Also, it is free, like we said. It'd be really nice if you helped your friends out. All you got to do is copy and paste that URL and just send it to your friends, right? Because again, it's free. Why not make everyone better? Yeah. Academic weapon, already a great teacher, not even sure. But yeah, you don't have to call me Miss, right? You can call me Brooke. I'm Brooke. Okay, so Newton's three laws. We need to know. Oh, my Scottish. No, I am not Scottish. Jake, we will save you. We've got you. Rashid, what's that, Brooke? No E. Okay, Newton's three laws. Help us out. What's the first one? Type in the chat. Chris, what you saying? Dave, cheers. So, an object at rest will remain at rest. An object in motion will continue to remain in motion at the same velocity. Yeah, that's right, Chris. Until what happens, though? Unless what happens? Newton's first law, Pranav, when there's no resultant force, the object is stationary. It will remain stationary. It's moving at constant speed. It will continue to move at constant speed. Yeah, nice. Yours and Chris's is probably the best there. Yeah, beautiful. Right, good. Good job, guys. Right, so the key thing we're looking at here is we can see that these forces are, what would you call those forces? Yeah, Imran, thank you. Here, the forces are balanced. So what we can see is that there is no resultant force. That's what Imran said. No resultant force. Okay, and to make sure we're good, what resultant means. Resultant, yeah, again, you can say they're equilibrium or they're balanced. Good. No resultant force. That was resultant, it's just a fancy way of saying like what's the difference in physics. So here, there's no resultant force, or that resultant force is zero. So that's why Newton's first law said if the forces are balanced, wait, hold on, Polito, you're a bit ahead of us. If forces are balanced, you will either remain at rest. So what that means, if it wasn't moving like 0 meters per second, if it wasn't moving before, it just stays not moving. Or it continues to move at that constant velocity. So good. So if it was moving at maybe 20 meters per second, it's going to keep moving at 20 meters per second. Yeah, good, good. Okay, what is Newton's second law then? What is Newton's second law? You can write the equation, or you can tell me in words. So potens, the acceleration object is directly proportional to the resultant force, F equal, yes, and inverse proportional to mass. Yeah, very good. That's a nice way to put it. Yeah, very good. Terminal velocity we'll get to in a second. F equals ma. Yeah, but careful, you can't write little f because you get given a formula sheet. If you write little f, they'll mark that as wrong. Is everyone good with that? A little f, that's a wrong equation. Yeah, good, 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 good. Lovely, good. So just make sure we're good. If you write in your test F equals ma, I know you might be thinking, oh, like Miss Chill, like Brooke Chill, we're just putting it on a chat, right? But it matters, right? So yeah, Anaya, just be careful. It has to be capital F equals ma, because that is wrong, okay? Be careful. Okay, so yeah, Newton's second law, like we just said there, look, potens right there, is resultant force is equal to mass times acceleration. So just please remember that F stands for resultant force. So what we're saying is if there is a resultant force, then there will be an acceleration. It will either speed up if it accelerates, or it will slow down if it decelerates. Okay, yeah, Dylan, just what you said about inertia. Inertia is the second law though. Inertia tells us that the larger the mass is, the harder it is to get to change its speed, the harder it is to get to accelerate. So just be careful, inertia is with the second law. So this word is starting to come up quite a lot more in that combined paper. What is inertia? Okay, so just remember, inertia tells us how hard it is to get something to change speed or to accelerate. So for example, if I asked you which has a bigger inertia, a bus or a bicycle, what would you write? What has got a bigger inertia, a bus or a bicycle? Nope, inertia is the rule is not enough. Yeah, easy, right? Yeah, Sophia, good. P, good. Lovely. Right, so a bus has a bigger inertia. It's much harder to get it to change speed. It's much harder to get it to change velocity. It's much harder to get it to accelerate, okay, because it's got such a bigger mass. Yeah, beautiful. Okay, one is a wee bit harder. How would you write Newton's third law? So how would you write Newton's third law? Hayden, they're the same thing. So for every action is equal and opposite reaction is a good way to write it. Yeah, two forces interact, they're equal and opposite. Michaela, yeah, that's good. Two forces exert a force. When two objects exert a force, they will exert an equal and opposite force on each other. Parf, yep, I like that one. Good. When two objects interact, the force exerted on each other equal and opposite. Dazola, yeah, perfect. Yeah. Yeah, playthings. I agree. You guys are like, You guys are like you guys are going to find this exam easy tomorrow. Yeah, good. So Newton's third law, I think it's just really important that you understand that it has to be on the same object. Okay, so just be careful about that because I didn't say that in your answers. I just want to make sure that it's not a confusion point. Okay, so if object A is how I would write it. If object A puts a force on object B exerts an equal but opposite force on object A, right? So sorry, did I misspeak? Yeah, I said that it has to be different objects, right? So forces must be equal in size, but they must be opposite in direction and they must be on different objects. Increase my volume. I'm up as loud as I can go, so maybe just use your computer. Luffy, you can see my wrinkles. That's cheeky. This is a free lesson. You could just log off now. Off you go. Okay. So Newton's third law to make sure we're good. What we're saying is, if I got a girl on a bicycle, there's the earth, right? We know that on the girl, you got the force of gravity, right? Gravity is that force trying to pull that girl down. Gravity, you might also see called weight, right? So weight is your downward force due to gravity. So if the girl gets pulled down by the earth due to gravity, the girl pulls the earth up due to gravity. Do we see that? I don't have wrinkles. Okay, so why do we not see the earth moving? For example, if I was to jump up, the earth pulls me down due to gravity, and I pull the earth up due to gravity. Megan, yeah, but they're the same thing for your GCSEs. What's the difference? Why would when I jump up, why do I come down? Why does the earth not come up to meet me? Yeah, thank you, Alex. The different masses, right? My mass is tiny, but the mass of the earth is really large. So even though we're exerting equal forces on each other, it's me that will always move because I have the lighter mass. Yeah, good. And this is to do with that inertia again, right? It's really hard to get the earth to move, but it's easy to get me to move because I've got a smaller mass. Yeah, I'm Irish. Yeah, for people saying I'm Irish, it's Irish. Can I say the law of example? Yeah, this would be your law. If object A puts a force on object B puts an equal but opposite force on object A. So I would learn it this way so you can write it. So then I would say if the girl exerts a force on the earth exerts an equal but opposite force on the girl. Could be another example. If a proton exerts a force on an electron exerts an equal but opposite force on a proton. So you see, it's quite a nice way to learn it because you just have to change the words around. Yeah, you can say F equals ma for Chelsea for Newton's second law. Okay, so to practice this now, the car is moving forward at constant speed. If the forward force is 110 newtons, what is the size of the backward force? Moonlight, easy, good, very good. Zoe, good, but you didn't write enough in my answer line. There's no answer lines if you get careful. A lot of you aren't giving me exactly what I need. Right. Okay, just make sure we're good here. I don't have an answer line. In your test, you might have an answer line that says newtons. I don't have that here. So 110 is not enough. Yeah, thank you. You got to say 110 newtons, right? 110 newtons, right? Because you've got to give it its unit. Okay. So the car is moving forward at a constant speed. Pippa, yeah, even if it was stationary, it'd still be 110 newtons. So cars moving forward at a constant speed. If the forward force is 110 newtons, the backward force must be 110 newtons, right? That was Newton's first law. Newton's first law told us if it's stationary or if it's at a constant speed, the forces are balanced, right? So the forces have to be balanced because it did say they're constant speed. Right. The forward force increases to 150, causes the car to accelerate. What is my resultant force? KAWTHAR is very good. Yes, thank you for being Pacific. Lovely. Only some of you are getting this full right. Iran, sorry, you're perfect. Oh, Subin, you're perfect. Adam, you're nearly perfect if it wasn't that little N. Yeah, lovely, good. So hopefully everyone's seeing that 40 newtons isn't enough because why? Why is 40 newtons not enough? Why is people saying that 40 newtons forward is getting the marks? What's the difference? Why do you have to say 40 newtons forward? Yeah, beautiful. Thank you. Yeah, it's a vector. Please remember, forces are vectors. So if you don't also state the direction, you're not going to get that full marks. Yeah, beautiful. Good job. Because remember, vectors have a magnitude and a direction. Remember, magnitude just means a number. So 40 newtons forward, yeah, or you can say 40 newtons towards the left. Good. So what we just said is this force has got increased to 150 newtons. So remember we said the resultant, that word resultant is just asking us what is the difference, right? So what is the difference? Yeah, good. DD, no, you don't have to say negative because it did state a direction in the question. It said backward in the question, do you see? Yeah. How do we get 40? Because if it's now 150 forward and it's 110 backwards, we just said there that resultant force just means difference. So the difference in 150 and 110 is 40. But the one, the forward direction is bigger. That's why it's 40 newtons forward. Yeah. Forward is what we just said there to the left. The way the car is facing, right? Forward. There's the front of the car. Do we see that? Yeah. Look, clearly, there's not going to be my driver here, right? Okay. Excel and AQA are like 90% the same. Yeah. Okay, the resultant force eventually decreases to 0, even though the car keeps a forward force of 150. Why? Bella, good, but you got to be a bit more specific. How did that happen? It doesn't mean some. No, it doesn't mean difference. Difference can also mean some, but you wouldn't add them together in this case, no. Yeah, Leon, thank you. Air resistance increases. Perfection, that's perfect. Yours was very good. Yes. So the resultant force eventually decreases to 0. So remember what the resultant force is, it means like the difference. So if the difference becomes 0, but the car keeps a forward force of 150. So we're keeping that forward force of 150, that's staying the same, but the difference becomes 0. What we're saying is that backward force must have to increase to 150 newtons, right? That's the only way for the difference to be 0, for the resultant force 0. So you're thinking, why would the backward force increase? Yeah, beautiful. Oh, it's not friction, no. The backward force increases because some of you said it's drag or, yeah, beautiful, air resistance. So we know the air resistance increases, and what you want to say, air resistance increases with speed. Yeah, good. Air resistance increases with speed. Yeah, that was a really nice answer. I can't pronounce your full name, but it's Land. That was perfect. So if you want to read the one that Land wrote there is good. So what we're saying is air resistance increases with speed. You know that, right? So think about air particles. If I'm walking, the air particles will barely hit me. If I start running, you might see my hair go backward because there's a lot more air particles hitting me. And if I was in a car and I set my hand at the window when I'm going so fast that my hand will fly backwards because that force of air resistance is so high. Okay. Someone said, what is air resistance? Someone help us out. What is air resistance? It's not friction, someone asked. It's not friction because friction doesn't increase with speed here. What we're saying is air resistance always increases with speed. Yeah, air resistance increase. What is air resistance? What is air resistance? Yeah, someone says drag. What type of force is it though? Yeah, that's what I want it. Thank you. Is it generous? Yeah, good. Air resistance is a contact force. Okay, so remember a contact force is a force where the objects have to be touching. So for example, if my car is moving forward, I know I've got all these air particles hitting that car, right? We know there's oxygen, we know there's carbon dioxide, there's nitrogen there. They're all hitting that car. But rather than draw all of these tiny arrows, what we can do instead is just draw one big arrow going backwards. That's going to be my air resistance. Okay. If it was friction, it should be between the tires and the road. So friction should be between the tires and the road. Okay. G9, not exactly. We'll talk about that in a second. Okay, next one. There are 3 equations to calculate acceleration on your data sheet. I just want to make sure we can practice using them and know which one to use when. So a bike accelerates from rest to 50 in 2 seconds. What is the acceleration? What equation are you going to use for the first one? So remember the free equation for acceleration, your formula sheet is F equals ma. You've got acceleration is your change of velocity over time. And you have v squared minus u squared is equal to 2as. So which are you going to use? The first one. Okay, we're all writing 25. I'm seeing 25 meters per second. I'm seeing 25 meters per second squared. Think about which one actually is. No, King, we're not going to post the answers on the workbook because that's not making you be a learner. right? The whole point is you're supposed to make your own notes and be an active learner, right? You're being an active learner. There's loads of research showing if we just give you the answers, you don't learn as well. Yeah, good. So acceleration, here I've got a time. So because I've got a time, I'm going to use this one. Acceleration is equal to the change in velocity divided by time. Okay, if you look at your formula sheet, so if I just pull it up quickly, if you look at your formula sheet, you can see there that it does say that fourth one down, that change in V, it stands for that change in velocity, right? So you have that on your formula sheet. It's that fourth one down there. And you should all have your formula sheet on you right now, right? So again, change in velocity, hopefully I'm thinking rest means 0 to 50. So the change is 50 over a time of 2, which is going to give me my 25, and it's meters per second squared. Please do not forget meters per second squared, right? Velocity is meters per second, right? The velocity is meters per second. Acceleration, we had to divide by a time again, so that's why it's meters per second squared. Yeah, good. Right, next one. A rocket accelerates from rest to 100 over 50 meters. Yes, I have a dog. He's actually being pretty chill right now. If we can get to, how many people are here right now? Look, I would have got 500 likes, not even. Look how many people here. If we get 1,000 likes, I'll bring the dog on. So remember again, just if you're new, if you want to type the chat, you just going to need to be a subscriber, okay? Okay, beautiful. This looks good. You remember myself for the last stream? Dog bribery. Always about that dog bribery, about all the bribery. Yeah, good. Lovely. So what we're thinking is, because I see a distance here, I'm going to use this equation. So what we're doing here is v squared minus u squared equals 2as. People get confused here because they don't know what the letters mean. But again, you look at your formula sheet. On your formula sheet, it literally tells you in words that's the final speed. It tells you in words that's the initial speed, right? It tells you that S stands for distance, okay? So what we're doing is our final speed accelerates from rest to 100. So the final speed is 100 squared. Take away the initial speed. It said rest, right? So rest is 0 speed. It's not moving. Squared equals 2 times the acceleration times by 50. Okay, so hope you're thinking, how do we simplify this? Sophia, yes, you can get away with drag, but air resistance is better. So right, 100 squared is going to be 10000. Take away 0 equals 2 times 50 is 100 times by A. And hopefully everyone's thinking, how do we get A by itself? And to get A by itself is that instead of multiplying by 100, hopefully you're thinking, what do we do to both sides to get rid of that? Multiplying by 100 means that we're going to do the opposite, which is divide. So what we do one side, we do to the other. So what you do on one side, we do to the other. Yep, you can write on the equation sheet in the exam. Good. Lovely. So your final answer is 100 meters per second squared. Yes, nice. No, Alex, not from Dublin. I'm from Korean. I don't know if you know it, but yeah, Korean. Yeah, 100 meters per second squared. Easy, guys. Beautiful. Yes, you get the whole equation sheet, that whole equation sheet. And for paper 2, it'll be all that back side. And you can write on it as much as you want. Yes, you can. Ollie, why would you not use this equation? It's the easiest one here to get our answer, right? Each one here, this would be a 3 marker, but because I didn't give you the unit, it would be a 4 marker. And again, here would be a 3 marker, but because I didn't give the unit, it would be 4 marker. G Brown, all of it is on will be on the triple paper, but if you want to just do space physics, it's right at the end. How do you know which one to use? That's what we're going for now, this guy. So again, what we're looking for is, there's my 3 equations, and here I saw the word time. Here I saw the word distance. And for this one, hopefully we see that I see force, right? I see force. Pranav, very good. Yes, Bella, very good. So because I see a force, now I'm going to use the equation F equals a M, or MA. Yes. Hashim, very good, but you wrote it a bit weird, but yes. Yes, good, right? So just for good, if you wrote 10 equals 100 times by A, you've lost a mark in your exam already, okay? You didn't lose all marks. So if it's out of 4 and you wrote A is 0.1, you would have got, out of 4 marks, you would have got 3. If you wrote 0.1 meters per second squared, right? That's 3 out of 4. What you should done is, hopefully everyone sees now, good. I'm not in chemistry, right? We're in physics. Physics mass has to be in kilograms. right? So 1k of cash is £1,000. Mathematic, if you don't know what drag is, don't worry. I wouldn't learn the word drag. Learn the word air resistance. Drag is kind of like a cop-out way of saying air resistance. So normally people write drag if they don't know if it's air resistance, if they don't know it's friction, if they don't know if it's water resistance. So no, I wouldn't bother learning about drag. Math failed. I did astrophysics. Right, so remember 1k is £1,000. So to get into k, what you do is you divide by 1,000. So if I want to get into k, I have to divide by 1,000. So what I should have wrote is F equals ma. That force is 10 newtons, is my mass is 0.1 times by a. Everyone see that? So to get a by itself now, because remember it's 100 grams, you put it in kilograms. Yes, Jude. So to get into a, we do the opposite of multiplying. The opposite of multiplying is divide. What we do to one side, we do the other. So your calculator should be 10 divided by 0.1. So 10 divided by 0.1, and we get 100. So 100 meters per second squared. Yep, perf good. Asher, speed is meters per second. So anytime you see the word speed or anytime you see the word velocity, that's meters per second. Because if you look at it, speed is a distance divided by time. It's a meter divided by a second. But acceleration is always a meters per second squared, because acceleration is that change in speed over time. It's a meters per second divided by a second. So that's why it becomes meters per second squared. Okay. Right. Next one. What if you get a question where it says in bold about vector diagrams? What would you do here? So again, this would not be on foundation tier. So this is only a higher tier question. Motor vec's coming up towards the end when we do electromagnets. Remember at the start, I gave you a list of what we're doing. So no, actually, if you use Pythagoras, you're going to get it wrong. You can't use Pythagoras, you can't do math here. So Pythagoras would actually lose you marks. You're not going to get any marks. It says in bold to draw a vector diagram. So what do you need to do? Make it a triangle. Thank you. Make it a triangle. So how do I make it how do we make it a triangle? Can I do this? What do you think? Yes or no? Thank you, chicken. Yes, good. Right? We can't do this because look, these triangles or those arrows, we can't add them like this. We can't add the arrows like this because they're tail to tail. You can only add arrows if they're tip to tail. So we have to move one of our lines. So I would probably move the bottom line. So I'm going to move the bottom line up to the top. So tip to tail. You can move anyone you want. Okay, you could have moved the 10 newton over. And then what I can see now is there is going to be my resultant force. We just complete the shape. Okay, so you complete the shape. Right, I can't use Pythagoras. So what do we have to use here? It says a vector diagram. Because it said in bold, you won't get any marks. How do we use a vector diagram? What piece of equipment? Thank you, Hashim. Yes, I need to take my ruler. Okay, if you use a vector diagram, you need your ruler. Okay, so what we're going to do? What do I do with my ruler? A scale. Good, thank you. So what I'm going to do with my ruler is I'm going to take my ruler, I'm going to place it along this line. Okay, I'm going to place it along this line. I'm going to measure the length of that line. Good. So hopefully you print the workbook like Riley has. Riley says the length of this line is going to be 2 centimeters. Okay, the length of that line is 2 centimeters. Yes, it's AQA. So what we're saying now is 10 newtons is equal to 2 centimeters in length. Okay, so now what would I do? What I do about, now what I do? Cube core, it doesn't matter if you use Pythagoras or not. Even if you get the right answer, they're not giving you marks because it said in bold, you have to use a vector diagram. This, normally they're kind of around 4 marks. If they're nasty, it'll be 5. Yes, Ebby, thank you. Measure the new line. So what I do now is I take my ruler and I'm going to place it on this line or place it on this line. But I probably want to measure on, I want to know the resultant force. So I'm going to measure it on my new line, my resultant force. So I'm going to put my ruler there and figure out what is the length of that line, that resultant force. And what did everyone get? Complete the shape is what it says. Okay, I'm saying 3.5 and 4. It's quite different. Did we print our work pack? Did we print it? We got 4.5. Okay, so let's say most of us are getting that we measured it to be 4 centimeters. So let's just say we've measured those people right. I've said it before, can't use Pythagoras because it says in bold, draw a vector diagram. They'll not give you marks if you do it. So if my line is 4 centimeters in length, what is that resultant force? What would we do? Yes, beautiful. Sakina, well, no, Sakina, what is that little end? Come on. Ebby, yes, good. Margaret, yes, good. Luca, good. Farah, no, you've lost a mark. Again, you might be like, oh, Chilbrook, but no, it matters. Okay, yeah, good. It's 20 capital N. Good. Because this side we had to multiply by 2. So this side I multiplied by 2 to get 20 newtons. Okay, so please remember, if you see the word vector diagram in bold, the first thing you need to look for is to make sure your arrows are joined tip to tail. Okay, they cannot be joined like this, and they cannot be joined like this, right? It has to be joined tip to tail. So if they're not joined tip to tail, you need to move them. The second thing is then that you need to take your ruler and find out what your scale is. Okay? And then the third thing is you just complete the shape. Normally it's going to be a triangle. So complete the shape or complete the triangle and then measure the length of your new line. Okay? I moved that line up because again, like I said, we can't join the arrows because they're tail to tail. Daniel, it's not that you'll lose marks. You can't lose marks in the test. You'll just not get the marks. So yeah, if you draw a formula triangles, if you have Pythagoras, you don't lose marks. You just not get the marks. They'll give you 0. Yeah. Rhea, like I said, Pythagoras is 0. Or like, do we zone out for like 10 minutes? How many times have I said, no Pythagoras, no Pythagoras, use a vector diagram. Vector diagram means use a scale, use a ruler, okay? Yeah, it has to be tip to tail, tip to tail. Dark, I'm not going to answer that one. Okay, next one. Next one is one of the required practicals. Some people asked about required practicals. We said biology, chemistry, and physics kind of like to do this thing. I would say it's not always useful, but it's good to talk about them. So remember, the independent variable is what I changed my experiment, what I've changed on purpose. The dependent variable, Pythagoras doesn't come up in A-level physics. Sorry, Pythagoras doesn't come up in GCSE physics somewhere. It's a maths, some you learn in maths. Dependent variable is what we measure, so it's what you've measured. And control variables are things that we keep the same. Sully, that's just the rule. It has to be tip to tail. Nico, yeah, you could get asked about the angles. Okay, so a student investigates how the height of a ramp affects the acceleration of a trolley. State the method to determine how the height of the ramp affects the acceleration of the trolley. So what would you want to write? Purple butterfly, if you scroll to start, I said what we're going to do in triple the end. Nope, this is F equals MA. This is paper 2 for AQA. Karen, this is AQA. If we come in new, I'm just going to start saying now, please go to the start because it's going to annoy everyone who's been here. So if you're coming in new, go to the very start of the video to find out what we're doing in this lesson. Yeah. Okay, what are we doing here? Okay, I'm going to change the number of wooden blocks. That's good. Change the number of wooden blocks. Why would I do that? Why would I change the number of wooden blocks? What am I telling them it's going to do? Yeah, thank you. Good job. That's going to change to change the height of the ramp. Good. So we're going to add blocks or take away blocks to change the height of the ramp. Good. Okay, now it says, we just said how we're changing the height of the ramp. How is that going to affect the acceleration down the ramp? So how am I going to measure the acceleration? Okay, yeah, we could use a light gate if you want it. Where would you put your light gate though? Where would you put your light gate? Middle, at the end, at the start? Okay, so how are you going to measure acceleration here? Tell me what equation you're going to use. What equation, that might help you out. What equation are you use to find the acceleration? What equation? Yeah, right. We're probably going to use change in velocity over time. So change in velocity over time. Okay, what velocity do you think it's starting at? What velocity is it starting at? Do we know that? Yeah, good. It's going to start at 0 speed, 0 meters per second. It's at the top of my trolley. So I don't need a light gate up there, right? I already see that it's at 0 meters per second, right? It's at 0 meters per second. So it's going to start at rest. It's going to move down my ramp to here. So we're going to find what's change of velocity of time. How I could either, like people said, I could either put a light gate here. And what a light gate is, just like a beam of light. And if you break that beam of light, what's going to happen is it's going to cause the sensor to detect the light was broken. If the light gets broken, it's going to start or stop a timer. But yeah, I would probably do what Isabel said. Yeah, good. Another thing I could do is just find out what that final speed is going to equal whatever distance it travels divided by the time it takes to travel. So how do I know what the distance is? How do I know what the distance is? How do we know what the distance is? My voice is grand. People checked it. Just maybe check your computer. Good. Okay. I need to use a ruler. Remember, in physics, you have to state the equipment. Use a ruler to measure. Yeah, good job. That was nice. Good job to measure the length of the ramp. Nice. What else equipment do I need now that I've not specified yet? What else do we need? I need a stop clock. Good. I need a stop clock, or I need a watch or a timer to measure the time for to go down the ramp. Yeah, good. Very good. Okay. What do we need to make sure then we're doing the same all the time? What things do we have to keep the same? Thomas, again, you can use a light gate if you want, or you could do this way. Yeah, stopwatch is fine. What we keep them constant here? Yep, same trolley, same massive trolley. Good. What else could we keep the same? I like the same massive trolley. That was nice. Yep, the same distance traveled, right? So we're going to make sure we always start it at the same point on the ramp, right? We're going to make sure that we always start at the same point. You're going to make sure, because we're starting at 0, I'm not going to push it. Okay, so you're going to make sure we don't push the trolley. We're making sure we use the same trolley or the same mass of trolley each time. Yeah, nice. Yeah, good. Very good. Okay, next one we're going to talk about is Hooke's law. Some of you have done since like year 7 and year 8. Okay, so what is Hooke's law? What is Hooke's law? The equation for Hooke's law, you're right, is F equals K times E. Good job. What is Hooke's law though? Good. What we're saying is the force. Yes, Krish, yours is perfect. Very nice. So what we're saying is the force is directly proportional to whatever that little E stands for. Remember, you don't have to remember what it is, because you can look for your formula sheet and you see my formula sheet tells me that little E stands for extension. Up until the limit of proportionality. Nice, good. Okay, so how would we draw this graph? So I hope you're thinking, I'm going to have my force against my extension. And what does directly proportional even mean? What does directly proportional even mean? Min, go ahead, just come back to it. What does directly proportional even mean? Yeah, we're going to talk about Adam in a second. What does directly proportional mean though? Good. Anytime you see that word, it doesn't matter what you're doing in physics, anytime you see directly proportional, you know it has to be a straight line that has to go through that point, and that point is going to be 0, 0, or your origin. Good. So it'll be a straight line through the origin. Good. That has to be a directly proportional. Okay. Someone said, what is the limit of proportionality? So what that means is, what we're doing here in Hooke's law, and the way I remember it is like Captain Hook, you know, from like Peter Pan. So Captain Hook, he's got a hook on his hand. So what you do is you hook masses to the spring, okay? So what he's doing is we're adding all these masses to the spring, and hopefully you're thinking, what's going to happen to that spring? That spring is going to keep increasing in length, okay? But what happens if I keep adding too many masses? You think about, you know, that slinky string you used to play with as a kid? If we add too many masses, think what would happen to your slinky string, right? Yeah, thank you, Isher. It's going to deform, right? It's going to deform. And what deform means is it won't go back to its original length. So if you ever had that like slinky string, you know that like they're really colorful and you would play with them all the time, right? You like play with them all the time. They're really colorful, you play with them all the time. And what would happen if you just like stretch it too far, you can't ever get it back in its little box. Yeah, so what we call that in the graph, you can see the graph starts to curve. So that point there where the graph starts to curve, that's what we call the limit of proportionality. So again, it makes sense because it's directly proportionality, right? So you just remember one word to get the other, directly proportionality. So what we're saying is the force is directly proportional to the extension up until the limit of proportionality. So what do we just say? Everyone says get deformed, which is nice. What will happen to it then if I try to put it back in the box? So if something goes beyond its limit of proportionality, what do you know about it? This guy, I feel you feel my pain right now. Yes. Again, if you're new, go back to the start to see what we're doing. Okay, what do we call that? Yeah, thank you, Erin. So if we go beyond the limit of proportionality, if we go beyond it, it will no longer return to its original length, right? And you might see that as plastic. If it becomes plastic, it is no longer elastic. Good. Or carrot core, good. Or we can call it elastic. So elastic deformation, be careful. If something is elastic, it will go back to its original shape. Deformed just means you've changed it. You've just changed its length. So yeah, what we call that is what you said there, Sanjay, good. It's called inelastic deformation. So it's inelastic now. Or you can say that it is plastic. Okay, so inelastic or plastic. Okay. No, for Hooke's law, you have to say that they're directly proportional. That directly proportional is really important in your answer. It has to be in your answer. Yeah. Not back to shape. You'd have to say not back to original length. Not back to original length. I just answered. Is that okay? Elastic deformation is anywhere in here. So elastic, if something is elastic, it will go back to its original length. Deformation just means you've changed it somehow. But elastic deformation means if you've changed it, it will go back to its original length. But if something is inelastic, it will not go back to its original length. You've changed it completely. Okay. Okay, next one is a spring has a spring constant of 50 Newton meters and a force of 3 newtons is applied. What is the extension? How do this? Yeah, beautiful. Good job, guys, right? Here we're thinking that equation F equals K times E. So it says the force is 3. It told me the spring's constant is 50. I have to multiply that by the extension. So I'm thinking, how do I calculate what the extension is? We do the opposite of multiplying by 50. And the opposite of multiplying 50 is dividing by 50. Good. So 3 divided by 50, yeah, beautiful, is 0.06 meters. Yeah, Zaina, good. Yes. Mark, yes, I said you could earlier. 0.06 meters. Why are we writing 0.6? Guys, we have a calculator. This shouldn't be something that we're going to get wrong in our test, right? So your calculator, which we're all going to double check right now, you should have 50 divided by 3, and you should get, what? Oh, I apologize. 3 divided by 50, sorry, we're dividing both sides by 50, and we get 0.06. I give you guys crap for not using a calculator, and I put it in the wrong way. Yeah, 3 over 50. Good. Yeah, 0.06. Okay, now we said plastic deformation is the same thing as saying inelastic. Plastic and inelastic are the same thing. Yeah. Okay, just make sure we're good where we got this equation from. Again, you can get the equation from your formula sheet, which we're all looking at all the time. You see the third one down, it tells you that F is force. It tells you K is spring's constant. So that's why we knew that number 50 was for K. And it tells you E stands for extension, right? It tells you that all on your formula sheet. Okay. Next one. It says the student keeps increasing the force applied to the spring. Eventually, the spring does not return to its original shape when the force is removed. Explains what happened. We've said this like 100 times now, so hopefully we know. Good. We've gone beyond the limit of proportionality. So we've gone beyond the limit of proportionality. What do we say it is now? Yeah, good. We can say it's been inelastic, deformed, or you can call that it is now plastic, okay? Because it no longer goes back to its original length. Good. So inelastically deformed, or that it is plastic. Good. The dotted line just shows you that because we went beyond that limit of proportionality, when we removed those forces, it no longer went back to its original length, right? Its original length might have been like 0 extension, but now there's going to be a permanent extension. It no longer goes back to its original length. Yeah? Yeah, Daniel, you can. I don't know what jeet is, no. Nizam, one is for energy and one is for force. So just check that in your formula sheet. One is for energy and one is for force. And the question asked about force. Yeah? Elastic means that, Jasmine, it does go back to its original length. So we said that earlier. Yep, EMBOC, that's what I said here, plastic. Yep. Yeah, okay. Next one is motion graphs. Okay, so really quickly, we're just going to look through things that you need to know about the motion graphs. So if it is a distance time graph, so please always look to see what the graph is first, right? Don't assume that you know what it is, right? If it's a distance time graph, what you can see is that the gradient tells about the speed, okay? So the gradient of these lines tells us the speed, and the gradient is the change in the y divided by the change in the x, right? So can someone tell me what is the speed of that red line? What is the speed of my red line on my graph? What is my speed of my red line? Beautiful, good. The speed of my red line is going to be the gradient of that red line. So it's going to be the change in y divided by the change in x. We can see that it starts at 0 and it ends at 10. So it's got a height of 10. And we can see that it's got a base of 2. So we did 10 divided by 2 to get 5 in beautiful units, meters per second, right? 5 meters per second. Beautiful. Okay, if I look at the blue line straight away, I know is going at a lower speed because it's got a less steep gradient, okay? And then here, I can see that it is stationary because at 4 seconds in time, it is 8 meters away. At 5 seconds in time, it's still 8 meters away. At 6 seconds in time, it's still 8 meters away. So it has never changed the distance away from me. So it's stationary or at rest, which is 0 meters per second. Good. Yep, some people are calculating what the speed of the blue line is. That's nice, good. What is the speed of my blue line? I can see that it's its height. The height is 8, divided by its base, which is 4, to give me 2 meters per second. Nice, good. Okay, the next one is our velocity time graphs. So if I look at velocity time graphs, I can see that here, the gradient of that graph is going to give me the acceleration. Okay, so the gradient of the graph is acceleration. Yeah, I don't do those, bruh. I don't know what that is. So the gradient of graph is acceleration. You like my Pearson, Sarah? Ah, yeah, I got them Pearson recently, actually. The gradient of graph is my acceleration. So can someone tell me what is the acceleration of the red line? What is my acceleration of the red line? Liffy and Nimra, you knew what I was asking. Yeah, Makala, good job. So what we can see here is I want to find the gradient. So we do the change in y divided by the change in x. So I can see it's got a height of 10. It's got a base of 2. So 10 over 2 is 5. Yeah, good job. Beautiful. Meters per second squared. Nice. Be careful, Sibin. Remember the units. 5 meters per second squared. Yeah, 5 meters per second squared. Farah, yeah, it's the helix up here. It does hurt when you get it done, I'm not gonna lie. Okay, good. So for the blue line, good job, we can see that it's going to be 2 meters per second squared. Okay, be careful. A flat line here means stationary, but a flat line here means a constant speed, right? Because we can see at 4 seconds, it's moving at 8 meters per second. At 5 seconds, it's moving at 8 meters per second. At 6 seconds, it's moving at 8 meters per second. Okay? Yeah, so what we're saying is the gradient. So can you tell me what is the deceleration? I can't spell. Decelerer, deceleration of the blue line. What is the deceleration of the blue line? Yeah, this can come out in foundation. Megan, we're going to talk about that in a second. What is the deceleration of the blue line? Charlotte, good. So Charlotte put it nicely. Charlotte says we're going to do 8/3. Good. So I can see it starts at the number 8, right? It starts at number 8. That's what it starts at, 8. And it drops down to 0. So that drop, that change in my y was 8. And it started at 7 and it ended at 10. So that change in the x was 3. Good. So what we do is 8/3. Be careful because some of you are getting it wrong. So if I do 8/3 in my calculator, I'm going to get the number of 2.6 recurring. So if you write 2.6 meters per second squared, that is wrong. Okay, that's not right. Please be careful. It's not 2.6 meters per second squared because the answer was 2.6 recurring. Please remember that is 2.66666. So I want to write that on my answer line. It's 2.7. Okay, please be careful. It's 2.7 meters per second squared. That is wrong. Okay, be careful. That is wrong. Yeah, 2.7. Yeah, 2.7. Well, I'm American. I'm American. I went to University in America, but yeah, I grew up in Northern Ireland. Okay, the last little bit that is for a higher tier only is to find what the distance traveled is. How do we find the distance traveled if you're doing higher tier? Yes, Molly, exactly what I wanted. The distance traveled is the area underneath the graph. Okay, so all you got to do is find out what the area underneath the graph is. Yeah, you can do a trapezium, or you can say that there is a triangle, find the area of a triangle, add it to the area of the rectangle, and add it to my last triangle. Good. Area under the graph, like we just said, is when you do distance traveled. Distance traveled is the area under the graph. Good. We're stressing about terminal velocity. We can talk about it at the end, okay? Okay, to practice what we just did. What is happening at y? What is happening at y? No, you can't write recurring decimals, keen in physics. You can't write 2.6 recurring, no. Okay, at y, good. We're saying this is a velocity time graph. So at y, you can see its velocity there is 50. It's 50, 50, 50, 50. So its velocity is always 50 meters per second. So my answer is going to be a constant, good, a constant velocity. Nice, Jasmine. Yep, nice, constant velocity. What is the acceleration of the place labeled x? So this is a harder question. This would be like a harder one to get. So I'm seeing 10, I'm seeing 10, I'm seeing a lot of 10s, I'm seeing 15s, I'm seeing 5s. So I'm seeing 10s, I'm seeing 5s, I'm seeing 15s. Question just means like at that moment in time, at that exact time. So hopefully you're thinking x. I want to see where it starts. X starts at 2. X ends here. It ends at 6. So remember, to find what the acceleration is, we've got to do what the gradient of that line is. We've got to do the change in y divided by the change in x. So what I can see is for the x, it went from 2 to 6, which means that it went up by 4. For the height, so I can see it starts at 10 and it ends at 50. So it went up by 40. So what we do is 40 divided by 4. So beautiful, guys. It's 10 meters per second squared. 10 meters per second squared. We'll do a break in, what, 15 minutes? We'll have our first break in 15 minutes. I don't know what you mean, Amina, by level up and not curve. Calc is short for calculator? Yes, it is. When did I write the word calc? Yeah. Okay, what is the displacement of the car in the first 6 seconds? How do you find displacement of the car in the first 6 seconds? Productions, things change. How do we find displacement in 6 seconds? Good job, guys. So remember, this is just a higher tier one right now. So the first 6 seconds, there's my 6 seconds. I need to find the area under this graph. So I want to find the total area under that graph. Okay, so remember, that's what displacement is, and find the area under the graph. Okay, some people are confused by the word displacement. Can anyone help out? What is displacement? What is it really asking? What is displacement? Help, because some people don't know. What is displacement? Sophie, can you tell me what you're confused about? Just saying you're confused is not helping. Yeah, beautiful. Distance, right? Displacement is just saying what is the distance, okay? Remember, displacement is just the vector. It means it's got a magnitude, a number, and a direction, where distance is just our scalar, which means it just has a magnitude, it just has a number. So just asking for the same thing. It's just asking for the distance. So just in the area under the graph. So hopefully you're thinking, for me, I'd probably set it up. You can do what you want, but I'd do 2 triangles probably and a rectangle. So for me, I would look at this triangle and I would do 1/2 of the base times the height. So I'm seeing 130 from Kayla, and I'm seeing 150 from Riley. Amina's 130. Imogen's saying 125. So for me, I do half the base times the height. That's 1/2 of 2 times by 10, which is going to be 10. So in here, I've got an area of 10. Here, it's a rectangle, so I know the area of a rectangle is just going to be the base times the height. So it starts at 2 and it ends at 6. So that base there is 4. The height is 10, so that's 40. And then for this triangle, I'm going to do 1/2 of the base times the height. So again, it's 1/2 of my base is 4, and my height was, again, going to be from 10 to 50, which is 40. So that's going to be 80. So what we do is we do 80 plus 40 plus 10, which is going to be 130 meters. Oh, Evie, just be careful with your units. 130 meters. Remember, distance is meters. 130 meters. No, Chloe, you don't have to, because deceleration means slow down anyway, so you don't need the negative. But Chloe, if you do your test, they'll give you the marks anyway. Yeah. Okay, what affects our braking distance? Bella, that is all perfect. Let me just read it. Bella, you said braking distance is everything you said. Yeah, perfect. Good job. Yes, beautiful. Oh, no, actually, be careful. You don't get any marks for saying alcohol. Good, good, good. Very good. A lot of us figured it out. Good. So remember, there's 2 things. There is a thing called stopping distance. And remember, the stopping distance is equal to the sum, you have to add them together, of your thinking distance and your braking distance. Okay? Thinking is what goes on your head, right? That's thinking. So that's what affects your head. So if I ask about thinking, that's when you say alcohol. That's when you say tiredness. But I didn't ask for thinking. The question clearly said braking. The only thing that affects the braking is about the car itself. Okay, it's not to do with you, it's about the car itself. So nice that people said if you're going at a higher speed, there's going to be a bigger braking distance. Nice that we said if the roads are wet, if the roads are icy, right, it's going to be a bigger braking distance. Yeah, Manny, nice. The condition of my tires, right? If my tires have a bad thread count, again, it's going to affect the braking distance. Yeah, good. And a nice one, Sarah, this is now you said, is about mass, and it's kind of what Bella said up there, but the mass of the car. If the car has a bigger mass, it's going to have a bigger, what Bella said there was EK, and that stands for the kinetic energy. Remember, kinetic energy is things that are moving. So this is like a higher tier answer. So the mass of the car, it's got a bigger kinetic energy. Because remember, kinetic energy is 1/2 the mass times the speed squared. So bigger mass, it's got bigger kinetic energy. So we need more work has to be done to stop the car. More work done by friction to stop the car. Okay, so that's like a higher tier answer if you could figure that one out. So it's good if you got that. So yeah, a cool job here is that I don't know if I told you guys last time, but a cool job is one of my friends from uni, he got hired by a Formula One race car company. So he gets flew around the world just to look at Formula One race car tracks to see that what tires should they put on the car, how lower or high should they raise the car, how fast they should go around turns. F1 is like Formula One, it's like race car driving. If you don't know what it is, it's obviously not a job you're interested in, for me. But yeah, there's a cool job if you're interested in. Here's a dream job. 130 meters. You could say forwards, yeah, but you didn't have to for this one. Right, okay, a lot of you earlier were stressing about vectors and scalars. Ashton, what's the crack? So let's talk through vectors and scalars. Okay, so this would be a 2-mark question if it came up your test. What's the difference between a vector and a scalar? What would you say? Krish, all of those are perfect. Yeah, very good. Very good, guys. Yeah, good job. So what we're saying is a scalar, how you'd write it perfect in your test, scalar has a magnitude only, but a vector has a magnitude and a direction. Okay. So yeah, nice guys. Yeah, nice work. Some of us are figuring out. And I know my picture is there now. Yeah, good job. This picture, I don't know if you've seen Despicable Me, but Despicable Me, have you seen the villain? Yeah, Vector, Livy. Yeah, and Despicable Me, the villain's called Vector, and he literally says, "I'm Vector," and I'm terrible at impressions, but he's like, "I've got magnitude and direction." No, you guys seen it? I don't know. Anyway. Okay, so just make sure we're good. What magnitude is? Magnitude just means size. It just means a number. Okay, so it just means like size or number. So if someone said like a magnitude 5 earthquake or a magnitude 6 earthquake, it just means the size. Okay, so a scalar, oh Layla, did they? That's awesome. A scalar has a magnitude only, but a vector has a magnitude and a direction. Okay, so for example, if I want to know the speed of the car, the speed is 25 meters per second. But the velocity is either positive 25 meters per second or negative 25 meters per second. So the positive 25 meters per second means it's going towards the right, and the negative 25 meters per second means it's going towards the left. Okay, so they're trying to show us about the direction the car is going in. Okay, yeah, lovely. Other types of scalars that you might want to talk about are time. That was a good one. We've got distance is a good one. Speed is easy to remember because they both begin with S. Velocity is a vector because they both begin with V. And other types of vectors, yeah, good. Another scalar is mass. Yeah, Mach, good job. Another vector is weight. Nice. Yeah, velocity is a vector. And then one we did in that last was displacement, that last question. So displacement is another type of a vector. Good. Yeah, another one, Krish, is momentum. Nice. Good. Yeah, Queen Zoe, good. Acceleration. And one we did earlier in the lesson that we had a right to the right. Yep. Lemes, good. Force. Forces are vectors. So you have to give them a direction as well. Yeah, you got to give them a direction as well. Yeah, beautiful. Okay, we'll do, what we do, 2 multiple choice questions and then 1 momentum question, and we'll take a break. I think that sounds good. Okay, so we're going to do a poll. And it should be 100% this poll because we have a formula sheet in our exams, and we have a formula sheet that is always in front of us in class, correct? So which one is the correct way to calculate momentum? Pop in the poll. There's a poll. Okay, go 5. Again, 100%, like no excuse. If you're getting this wrong, like you may as well just tap out for tomorrow because you have a formula sheet. It's there, okay? So you should be looking at your formula sheet. How do you calculate momentum? How do you calculate momentum? Okay, 5, 4, 3, 2, 1. Okay, yeah, on our formula sheet, which is shocking. How did that 12% you picked A? You just need to cut your losses now. I'm sorry. Okay, momentum is mass times velocity. Please be careful, okay? Momentum is mass times velocity. Right, next one. Which is the correct unit for momentum? Okay, is it A, is it B, or is it C? Go. And this is only higher tier. So I guess if that 12% was a foundation tier, then you're grand. I'm sorry, I shouldn't have bullied you. If the 12% was a foundation tier, I'm sorry. Okay, which one is momentum? So it was covered there a little second by our units. Oh, even though they're now, just the thing was in the way. Okay, you got 5 seconds. 4, 3, 2, 1. What are we saying? Yes, beautiful, lovely, 85%, good. It has to be this because remember what we did, momentum is a mass times a velocity. Mass is in kilograms and velocity is meters per second. So that's why it's just kilograms, meters per second. It's not divide, Sophie, because we didn't divide anything, right? You multiply. When you multiply, you just put them beside each other. Yeah, when you multiply, you put them beside each other. Okay? So because it was a mass, which is in kilograms, times a velocity, that's why you just keep them beside each other, because you times. It's only like, say your equation was speed is distance over time, because it's a meter over a second. That's when it becomes meters per second. This is multiply, that's why they're beside each other. Yeah. Okay, we'll do this one question, then we'll take a break. So the law of conservation of momentum, you need to know, okay? If you get any question, if it's a 5 marker, if it's a 4 marker about momentum, you will always get 1 mark if you write this line. The total momentum before has to be the total momentum after, right? Total momentum before has to be total momentum after, okay? We know momentum is mass times velocity. So it says a truck has got a mass of 1,500 kilograms, moving at 3.5, collides with a stationary car of 800. They stick together and move together. By conserving total momentum, what is the velocity of the combined masses? So again, this is higher tier only. Okay, for me, I would draw a picture. So I've got a truck. So I'm seeing some answers are 2.23. I'm seeing 2.3. I'm seeing 2.28. The truck, mass 1,500, moving at 3.5 meters per second. Collides with a car that's stationary. Hopefully you're thinking, what does stationary mean? It means it's not moving. So 0 meters per second, and it's 800 kilograms. And it says what's going to happen is they're going to stick together. So my truck is going to stick to my car, and they're moving at some speed together. So I want to figure out what speed is that they're moving together. Okay, so hopefully I think momentum's conserved. So I think my momentum before has to equal my momentum after, right? They have to be the same. So I need to figure out what is that momentum before. So I've got a truck that's got a mass of 1,500. Its velocity is 3.5. And I've got a car of mass 800 and its velocity of 0. So the total momentum before is going to be 1,500 times 3.5. That I don't know off my head because my mental math is shocking. So we do 1,500 times by 3.5 to get what that momentum is, 5250. So 5250, and this is 0. So when we add them together, the total momentum before is 5250. I'm also seeing a 6.6 as an answer. So this is my total momentum before. So everyone figures out if the total momentum before has to be equal to the total momentum after. So the momentum after is 5250. That's my momentum after. And that's going to equal the mass times the velocity. What is the mass after? Because they're both stuck together. So how are we thinking? How do we do the mass after? Yeah, it'd be good. They're stuck together. So I've got a 1,500 and an 800 stuck together. So the total mass is 5, 6, 7, 8, 2,300. Yep, row can. Good. 2,300 times by V. Good. So if I want to get V by itself, we think, what do we do to the 2,300? The opposite of multiplying is dividing. That's how we get rid of it. So to get rid of it, we have to divide by 2,300. And what we do to one side, we do to the other. So in your calculators, what we're doing is we're dividing by 2,300 to get what that velocity is. And it is 2.28 or 2.3. Yeah, Imogen, perfect. So 2.28 meters per second is fully right. 2.3 meters per second is also fully correct. Okay, so good job for the first or the second person there. I saw put the answer in the chat. So 2.3, yeah, Bradley, 2.3 meters per second. Zinni, I would always say for AQA, I do 2 decimal places, which is better, 2 decimal places. Why 2,300, Lori? Because it said they're stuck together, right? They're combined after. They're stuck together, so they're moving as one object. So they're moving as one object. Yeah? They're moving as one object. So momentum before has to be momentum after. No, kilo is small letter, sorry. Sorry. It's a small letter times G. Yeah, kilo is small letter. Would it be 2.29 because it's recurring in the 8? No. So if you just look at it there, it's 2.2826 all recurring. So it's like it basically goes 2.2826086 and then it goes again 826. So no, it's not. That's not just it's not 2.28 recurring. It's 2.2826086956521 then 8260869. Do you see? Yeah. Yeah, Taylor, that's actually a triple question. That's about impulse. If they didn't stick together, then yeah, you'd have to do them separate. But you couldn't do the question then they're separate because you'd have to know the velocity of one of them after. Yeah. Okay, we are going to do sound waves after the break. So I'm going to give you, we're going to give long because we only, if we're doing combined, we're going to probably only have like another hour of lessons. So if you're here for combined, you're probably only going to be here for 1 more hour. So it's not very long, okay? Because the last bit's triple. So we're going to do, we'll do an 8-minute break so that you can put on the kettle if you want a cup of tea. Okay? So it is currently 5:15. So I will see you at 20. Nope. I'll see you at 5:23. Yep. So you got enough time to go to the toilet, put on a cup of tea, get some water, get a sweetie. Got an 8-minute break. Yes? 8-minute break. We're nearly at 1,000 likes. If it gets to 1,000, I'll bring my dog on before the 8 minutes. Yeah, I'll bring the dog on before the 8 minutes. So if you come back a bit early, you'll see him. Maybe if he's asleep though, because he went to the park today. He had quite the day, so yeah, he's just like he's tapped out on the couch right now. Okay, I'm going to run to the bathroom as well. So 5:23. I'll see you in 7 minutes now. Okay, see you in a sec. What's the crack? Got your cuppa? You ready? Raya, what do you mean finishing the content? Yeah, we're going to finish the lesson. We'll finish the lesson. Baba, you come say no. Come here. Come here. He's dead. He won't come. Baba. Baba. Nope, he's dead. He's dead to the world. I'll try when he's up and about, I'll bring him over, but he's dead. Yeah, he's dead. Okay, first question. Revive him. Right, what type of wave is a sound wave? What type of wave is a sound wave? Should be easy, hopefully. Yeah, nice, good. Yes, it's combined and triple longitudinal. If you're saying transverse, you need to know this one. It's basically the only longitudinal wave you need to know about if you're doing combined. Right, it's the only longitudinal wave you need to know about if you're doing combined. Longitudinal sound waves. Please don't forget that. Right, how do you hear sound waves? No, Mohammed. Yes, Angie, oscillations are parallel. They're oscillations, thank you. The oscillations are parallel to the direction of energy transfer. Okay, don't forget that sound waves are longitudinal waves. Yeah, thank you, content. That's what I wanted. Sound waves are heard because the vibrations have to enter your ear. The vibrations make your eardrum vibrate. Okay, the eardrum vibrates. Just have to make sure you have the word vibration in there. Okay, so please make sure if you talk about any type of sound waves to make sure that you get the word vibration there. Sound waves makes your eardrum vibrate. Sound waves are longitudinal waves. Hannah, please don't do that. Sound waves are longitudinal waves. Okay. Right, what is the range of human hearing? So far, these are both 1 mark questions. First one was longitudinal. Second one is that your eardrum would vibrate. Yep, Chris, beautiful. Your range of human hearing is go from 20 hertz. Be careful how you write hertz. Yep, Hazel, beautiful. Up to 20,000 hertz, right? That's the range of human hearing. Good. The range of human hearing. Nice. 20 hertz to 20,000 hertz. Jude, triple and combined. Yes. Yes, yes, Jason, this is still combined. Yep, 20 to 20,000 hertz. Good. Okay, next one. Oops, I kind of covered the question. What is the frequency if 10 waves pass a point in 2 seconds? So it says, sorry, it says 10 waves pass a point in 2 seconds. How would I calculate the frequency? Yes, combine needs to know. How do we calculate the frequency? So I'm seeing a lot of 5 hertz. Good. Right, when you know the definition of what frequency is the number of waves in what? The number of waves in 1 second, right? Frequency is a number of waves in 1 second. So if I have 10 waves in 2 seconds, I want to know how many waves are in 1 second. Hopefully you're thinking this side, we divide it by 2. So this side, I divide by 2 and I get 5 waves. Good. So if I want to know the frequency, then I just write 5 hertz. Good. Beautiful. Good. Period is 1 over the frequency. So period is the time for 1 full wave. It'd be 1 over the frequency. Yeah, good. Okay, so key thing, yeah, the key thing is here, you see that the energy is moving outwards, right? The energy is moving outwards, but the particles don't move outwards, right? If I look at a single particle here, if you focus on a single particle, that particle is just vibrating parallel to that direction of energy transfer, okay? So remember, what's happening is you cannot say in your exam the particles move. You have to say the particles vibrate and the energy it gets transferred along, right? It's not that a particle at my voice box right now is shooting out towards your ear. The vibrations are carried towards the microphone and those vibrations are carried along to your speakers, okay? So it's the vibrations that moves, okay? Okay, next one, how to calculate the time period. And sorry, I covered the question. How do we calculate the time period if we just calculate the frequency? Yep, good. Tangle dream, nice. If you look at your formula sheet, you can all see that equation. It says that time period is 1 over the frequency. Good job, Harry. So time period is going to be 1 divided by 5, beautiful, which gives me, yep, Drew, nice, 0.2. And what is the unit for time period? No, you don't, Abby. What is the unit for time period? 0.2 what though? Yeah, Cooper, beautiful. 0.2 seconds, because time is always measured in seconds. Good. Time period is the time for one full wave or one full cycle to pass. Good. Okay. How many waves are in my diagram? Should be hopefully just make sure we're good. Yeah, Bobajuk is done. When he's up Jonathan and Lively again, I'll put him back on. Right, I'm seeing loads of freeze. Yes, good. Rusky, good. Yes, good. Zachariah, good. Caitlin, good. Yeah, beautiful. There are 3 waves in my picture. Because look, if I start here, I go for 1 peak, 1 trough, there's 1 wave. 1 peak, 1 trough, there's 2 waves. 1 peak, 1 trough, there's my 3 waves. Good. What is the wavelength? What is the wavelength? Remember, wavelength is the distance of 1 full wave. This is 1 full wave. S, it's not me ban you, it's the moderators if you say something inappropriate. Audrey, good. Good, Hannah. But Hannah, give me a unit. Yes, nice, nice. Yeah, Zachariah, perfect. Nope, some of us are getting 2. Why are we getting 2? Wavelength, remember, what's that saying? Is the distance of 1 full wave, right? We're looking for the distance of 1 full wave. So there's my 1 full wave, and I go down to see what that distance is, and it's going to be 4 centimeters, right? 4 centimeters, my unit there. 4 centimeters. Yeah, or you could do peak to peak, or you could do trough to trough, either one you want. Yeah, so I could do, there's my 1 full wavelength, or like people said there, I could do from a peak to a peak, which is also fine, but it's a bit harder in this diagram. So what you're doing there is you're going from, you'd be going from 5 up to 9, which again is going to be my 4. Yeah. Okay, next one. What is the amplitude? S, just focus or forget about it. Move on. What is the amplitude? What is the amplitude? Cooper, very good. I am like very good. Yeah, nice definition. Good. Yeah, good, good, good. Amplitude, remember what that stands for? It stands for the maximum displacement. So nice you got that. The maximum displacement from the equilibrium. Right? So remember that equilibrium is just that middle line. So what I do first is find where that middle line is. There's my equilibrium. And I want to know what the maximum displacement is. So it's just asking what is that maximum height from the equilibrium, the maximum distance from the equilibrium. And hopefully everyone saw it's 3, and then again it's centimeters, 3 centimeters. Yeah, good. Good, good, good. 3 centimeters. Can you say rest position? Yeah. Equilibrium's better because technically it's not at rest. It's not that it's not moving there, so be careful. Yeah, so equilibrium is better because rest position makes you imply that it's not moving. So yeah, call it equilibrium. Equilibrium. Okay, next one is we're going to go over our transverse waves. Okay, so transverse waves is the opposite. It's when the vibrations are perpendicular to the direction of energy transfer. So for example, if I have a light ray coming down, all the vibrations are going to be perpendicular to that direction of the direction of energy transfer. Okay. You need to know that all EM waves, you can write capital E, capital M in your exam. All EM waves are electromagnetic waves. Okay. And they're all transverse waves. Okay, so it's a popular, especially in foundation tier, as a popular multiple choice question asking you about what all EM waves are. They're all transverse waves. And another popular question in multiple choice in foundation tier is asking you what speed they travel at. You make sure they know that they all travel at the same speed. They all technically travel at the speed of light, which academic weapon is that number. Yeah, good job. So yeah, technically all travel at the speed of light, which is that number that we're all quoting there, 3 times in the power of 8. Right, so let's go over our waves that we need to know. What's different in my picture along this diagram? What is changing from left to right along my diagram? What is changing from left to right? No, you don't need to know that number, no. Good. Up here is going to have a really high frequency. Good. It's really high frequency. Yeah, good. Nice. People said about the wavelength. Good. It's going to have a really small wavelength. Where's the most energy? Left or right? Yeah, good. The high frequency, yeah, good job. The high frequency is where we have that high energy. So there's almost energy waves. Just make sure everyone's a good. Remember, wavelength, you can say is peak to peak or trough to trough. So there would be my one wavelength. And we can see here, the wavelength is much shorter. So that's how we knew the wavelength had decreased. We also know that it's much higher frequency. And how we tell by frequency is because all our waves are really squished together. So over here is really high frequency because all my waves are really close and shift together. Okay. So the highest energy one, the most dangerous one, hopefully everyone is aware of, is going to be my gamma rays, right? They're the most dangerous, the most high energy ones, okay? And the lowest energy ones, Pravan, good. The lowest energy ones, the ones that are really safe, that we used all the time, are going to be my radio waves, right? Because we use radios all the time. We have radios in our cars, okay? We use them for communications. They're really safe. Okay, the next most dangerous one is going to be my X-rays. X-rays are really dangerous. They're really high energy. Yep, Sophia, good. And the next low energy one there is my microwaves. We know they're low energy because most of your homes have a microwave inside them because they use microwaves. Good. Okay, the one right in the middle is always going to be visible light. Okay, and the last two is infrared and UV. Okay, so what you're thinking, ultraviolet light is quite dangerous because what you're thinking about something your parents told you about, and then infrared is less dangerous because we use them at the time. So why are UV dangerous? What do they cause? Hopefully your parents told you about it. You're not supposed to use something because of the UV rays. What does UV cause? Yeah, Nadia, beautiful. UV rays cause skin cancer. Okay, think about those sunbeds. They use UV beams. Okay, so if you say cancer, you get the mark wrong. Okay, so Lily, be careful, and Lily, Bacon, be careful. If you, Samuel, careful. If you write cancer, if you want to write cancer is wrong, you have to write skin cancer for UV. You have to write skin. Yeah, again, you can draw premature aging is another one as well. Okay, why are X-rays and gamma bad? What can you say about those? Why are X-rays and gamma bad? Yeah, these ones you can say for cancer. So these ones you can say for cancer. Don't say ionizing. Ionizing is a paper one thing. Forget about ionization. That's a paper one thing. Right now, you just want to talk about cancer. Okay. So you can say they cause cancer. Yeah, random. You can say they cause mutations to your DNA. Yeah. Megan, don't say highly ionizing because technically they're not highly ionizing. Alpha is highly ionizing. Don't confuse alpha radiation to what we're talking about right now. Okay. Okay. Yeah. So they cause cancer. Good. Okay, can someone tell me, we just said what radio waves were used for. We said we used them for communications. What was microwaves used for? What were microwaves used for? Alex, the ones that cause cancer. What are microwaves used for? Yeah, we use them for cooking our food, right? We all have a microwave inside our homes. Good. What is infrared used for, or IR? What is infrared used for, or IR? Yeah, good job. So infrared is actually used for those little heaters. We use infrared for heating. Good job. Heaters. Yeah, good. Or we use them for night imaging goggles. So you know at nighttime, obviously you can't see anything because there's no light. So we can use night imaging goggles. And what they do is they show up anything that's really hot so we can see it. Yeah, good. Okay, visible light. What do we use visible light for? Yes, Alina, they can. We'll get to that one in a second. Good. Jen, one they really like in your test is optic fiber communications. Right, so that's like your internet, your BT internet, yeah, fiber optic. So like if someone said you've got fiber optic or do you have fiber optic? One they really like is fiber optic communications. Yeah, good. We also obviously use them for eyesight or photos or photography. Right, photos or like photography. Good. No, you don't, Chelsea. Okay, UV, remember the bad thing is skin cancer. Please make sure you say skin, right? Skin cancer, skin cancer. Okay, what is a good thing for X-rays? What can we use X-rays for that are a good thing? What is a good thing for X-rays? Medical imaging, yeah. Imaging broken bones, good job. So we use the medical imaging, we can use the imaging Broken bones. Okay, just some way you might see the word broken bone in your chest is a fracture. It's just a way you might see a broken bone. And what can we use gamma for? They are really dangerous, really high energy. I saw some people wrote that we can use gamma rays for sterilization of medical equipment. Which is nice because those gamma rays, they can get through. Yeah, good. Another one we can use is for that radiotherapy. Yeah, nope, not chemotherapy. That's chemistry. Radiotherapy. Yeah, so we can use them for sterilizing medical equipment. So what that means is we can bomb them through the equipment. Lily, give me 2 seconds. We can push them through the medical equipment without having to touch it, right? We can kill any bacteria or any viruses on the equipment to make sure that they're safe to use. One thing about imaging broken bones, again, remember that the x-rays, they can get through skin, they can get through flesh, but they are stopped by that bone, and that's why we can image the bone. Yeah, good job. Someone asked what ultrasound is. Ultrasound is just a sound wave. Ultrasound is a longitudinal wave with a frequency above 20,000 hertz, so we can't hear it. Ultrasound is just a sound, right? It's just a sound wave. But these ones are all our transverse waves. These ones are all our electromagnetic waves. They all travel at the same speed in a vacuum. Good. Okay, make sure we're good. What's my missing gaps? This is like a common question. What's my missing gaps? Good. First one's going to be radio. Nice. Radio, visible X-ray gamma. Radio, not visible X-ray gamma. Nope. Radio, infrared. Yeah, good. Radio, infrared. Good. And then X-rays. Nice. And then gamma. Nice. Easy. Which one has the longest wavelength? P and S waves is triple, Theo. What is the longest wavelength? Oh, someone's writing gamma. Good. The longest wavelength is radio. Remember, look back. The longest wavelength there is radio, right? Radio is the longest wavelength. It's one with the least energy. Which one has the highest frequency? Which one's got the highest frequency? Leon, good. PN, good. Lovely. It's going to be gamma. Has our highest frequency. Nice. Which one can our eyes detect? Rose, good. Which one can our eyes detect? Yep, moon, good. Good, very good. Yeah, it's going to be my visible light. Nice. Which one can cause skin cancer? Skin cancer. Yeah, good job. Tingle bot. Yeah, good. UV, nice. Ultraviolet or UV is the only one that causes skin cancer. Good. Nope, Heidi, you don't say gamma or x-rays. Please make sure you're good with that. Gamma and x-ray, you just say for cancer. Skin cancer, they always just want UV. Yeah, skin cancer is UV. Okay, one of the practicals. So one of the practicals might be that you get a Leslie cube. Okay, what a Leslie cube is that it's just a cube and we fill it up with hot water, right? So all we do is here, we pour in hot water so that obviously all of these faces have hot water touching them. Okay, how do we do the experiment? What is the IV, CV, and DV? Kira, yeah, what is the IV, CV, and DV? So tell me, what's IV, what's CV, and what's DV? So the independent variable is what I've changed. Good, Angie, we've changed the color of the surface, right? So what we've changed here is I've got a matte black surface, a matte white surface. Matte just means dull, right? So like dull black, dull white. I've got shiny silver, I've got shiny black. Good. What is the thing that I'm measuring? What's my DV? What am I measuring here? What, Lucas? No, I'm not measuring the temperature technically. What is it? Look, it's got a piece of equipment here. Yeah, good job. We're measuring the amount of infrared radiation emitted. Good, good. Now, what things that are important here would we keep the same? What things would it have to keep the same? What things would it have to keep the same? Good, Tabby, that's a really important one. Yeah, good job. One thing that's really important we keep the same is the distance to the detector. So we move that detector around to different places. We need to make sure we keep that distance between the faces and the detector the same, right? Because if we're closer to it, there'll be more heat. Like if you're closer to a fire, it's going to be hotter. If you're further away from a fire, it's going to be cooler. So to make sure I keep the distance the same. So the distance between, so the volume is not 1 because it's 1 cube. It's 1 cube of water, so the volume is not 1. Distance between the detector and the faces or the surfaces. Again, mass of block's not 1 because it's already controlled because there only is 1 block. There only is 1 block filled with 1 water. Temperature of water is not 1 because again, it's only 1 thing of water. So it's clearly all the same temperature. So that's not 1 either. This is combined and triple. What is something else we keep the same? Thermometer you can't use here because we're measuring the amount of that's been emitted from the surfaces. So no, you can't use thermometer here. Where would you put the thermometer? What else could we do? No, amount of water, volume of water is still not 1. Remember, we said there's only one. There only is 1 thing of water in here, right? There's not loads of different things of water. Size of cube is close, but it's not exactly right. Good, Pranav. I want to keep the surface area. The surface area of the faces is the same. Yeah, the surface area of the faces needs to be all the same. But one that's really important, look, let's say I've got hot water in here. It's hot water, but again, that's kind of controlled because it's a cube, right? Cubes all do have the same size of faces. So again, that's kind of cubed. But think, when I put the hot water in here, it's already hot at the start. And if I go and record this face first, what's going to be hot? What's going to be different when I go over here and record this face? What's the problem here? Yeah, because it takes, the temperatures will be different. So what should I do to control it? How can I control when I record the IR radiation? Yes, thank you. We got there. Your fave Egyptian. Good. We're going to make sure that we measure at the same time. We're going to measure the infrared radiation at the same time. So the only way to do that is I actually need more than 1 infrared detector. I need 4 infrared detectors, right? Because we need to be measuring all at the exact same time, right? Because we don't want to measure one face and then 5 minutes later go measure the other face because it's already going to have cooled down. So we need to make sure that it's not going to cool down because of the face. Nope, this is combined. It's not going to cool down because of the face. It's going to cool down because it took me too long to get around to the other side. Okay. Okay, just make sure. What's your prediction? Which side is going to emit the most infrared? What do you predict? Which side would emit the most infrared? Which side? If the chat's distracting you, someone wrote there in chat, just block the chat. Don't look at it. Which side is going to emit the most infrared? Good. Thank you, James. You need to say matte black. It's the matte black side. It's not just the black side because there's 2 blacks, shiny black and matte black. So you make sure that you say it's the matte black side because it is the best absorber of the infrared radiation and the best emitter of the infrared radiation. Because remember, what we have in here is we have water. That water is hot. So the black surface is going to absorb all of that infrared radiation from the water, and then it's also going to emit all of that infrared radiation from the water so that the detector can pick it up. Yeah, good. Nice. David, be kind. Right, next one. What is my equation to calculate wave speed? Megan, kinda, but it should be a detector. I'm told you when Baba is up and about, I'll bring him over, but he's having a time. He went out for a long walk today. What's that FL? Yeah, good. Wave speed is equal to frequency multiplied by wavelength. Good. Wave speed is equal to frequency multiplied by wavelength. Okay, how do we find the speed of water waves? What equipment do we need and what measurements we need? So what do you think? How do we find the speed of water waves? Caitlin, you take a break and come back to it. It's recorded. You can watch it anytime you want. Ripple tank. Yeah, good job. So I need a ripple tank. Nice. And your ripple tank, what else we need? So what we have here is a ripple tank. Hopefully people remember it's just a tank, exactly that. And we have this little thing that vibrates. And what it does is it makes those water waves And then it's normally connected to some type of light source so that we can get a shadow of those waves on the ground, right? We want to get a shadow of those waves on the ground. So we have our ripple tank. So I want to measure the speed of the water waves. Yep, I need a ripple tank. I need a meter ruler. And I need a timer. Thank you. Good job, Lila. So what do we do? How do I find the speed of the water waves? To find the speed, I need to know their frequency. I need to know their wavelength. So how do I find the frequency and how do I find the wavelength? I can record it on my phone. Yeah, you can do it if you want. There is no frequency generator. I'm finding the frequency of the waves. Frequency of the waves. Good. Measure the wavelength using a ruler. How do that? Yeah, good. So what I could do is I could measure the time for 10 waves to pass. Because if I try to measure the time for one wave to pass, that's going to be so quick that I'm never going to get it. So I'm going to measure the time for 10 waves to pass. I'm going to divide by 10 to get the time for one wave to pass. Okay, so now I've got the time for one wave to pass. How do I get the frequency? I've got the time it takes for one wave to pass. How to get the frequency? Yeah, good, Pranav. So if I know the time to get one wave to pass, because time is 1 over frequency, I can say then the frequency is going to be 1 over that time. Yeah, beautiful, good. Okay, to measure the wavelength. Yeah, good job. Yep, Pavan, good. Measure the wavelength. I'm going to measure the distance across 10 waves and divide by 10 to get the wavelength. And then to find the wave speed, I just do frequency times wavelength. So down here, all I can do is I can take a picture of my phone, or I can just measure it with myself. There's the start of the wave, and then see where 10 waves later is, and measure that distance using that ruler. So I'm saying it's measure the distance using the ruler or the meter ruler, and measure the time using the timer, or I could say a stopwatch. Nice. You should probably write the word divide. Yeah, good. What causes the bar to vibrate? Megan, is connected. Basically, it's like a vibration generator. You don't need to know that. You just need to know that a ripple tank already has that connected. And the ripple tank is just going to vibrate up and down because it's connected to this like signal generator. And it's going to, when it vibrates, it's going to hit the water and make the water vibrate. Yeah. Hey, blocks, just tell me what's wrong and I can help out. Okay, next one. These are my data. What is the speed of the waves? Yes, cube core. Good. Hannah says 1.5. What are you thinking? 1.5, 1.5, good. So the speed of waves is just the frequency times by the wavelength. The frequency is 5, the wavelength was 0.3, so it was a really nice question just to get 15 meters per second. Nope, 1.5 meters per second. Good. 1.5 meters per second. Annie, that's what we said. Measure the time for 10 waves divide and divide by 10. Because one wave is too short a time. You can never record the time for one wave to pass. So yeah, 1.5 meters per second. Yeah, this is still foundation as well. No, we can't do that one for wave speed because you don't know the distance they travel and you don't know the time it takes one wave to travel. Yep, Samaya for addition and higher. Okay, next thing we need to know. So this is higher tier only. So this one says that we need to know what reflection is. So remember, reflection is when light waves hit surfaces, they're going to get reflected. So what we always do, remember, is that we draw a normal here. So we draw a normal to your surface. So remember, the normal is always at 90 degrees to the surface. And what we do is that our angle of incidence, because the incident, remember, is that incoming ray, the angle of incidence is always equal to the angle of reflection of the outcoming ray, right? So that's how we see things. So hopefully you remember in Key Stage 3, you said that you want to see things because I can see an object because the light ray reflects into my eye, right? No, there's not, Dynasty. The light ray reflects into my eye. Okay, refraction, we need to know, is the change in direction of light when it passes into some medium with a different densities. Okay, they got different densities. So can someone tell me here what's going to happen when my light ray travels from air into water? What's going to happen to that light ray? Jonathan, what's going to happen to that light ray? Annie, that's what we said. It's going to slow down. Good. So we know that it's going to slow down when it enters the water. And what is it going to do? How's that path going to happen? What do you mean mucus are normal? Where is the normal? Where is the normal? Thank you, Abdullah. Good. It's going to just go straight through, because what you need to know about is if a light ray enters at the normal, if it ever enters along the normal, it just goes going straight. So if it enters along the normal, it just keeps going straight through. Good. However, in this one, here's my normal. My normal is at 90 degrees to my boundary. Here's my incident ray, my incoming ray. When that ray travels from air into water, like you all said, it's going to slow down. And a nice way to remember it is fast. Okay? If it is traveling faster, it always bends away from the normal. And if it is traveling slower, it always bends towards the normal. Okay, so this is what would happen if it went straight through. So going to tell me, is it going to go option A or is it going to be option B? Look at fast. What's it going to do? Is the light ray going to go option A or option B when it enters water? Option A or option B? Yeah, beautiful, good, right? Because it's going to slow down, it's going to bend towards the normal. Clearly B has moved closer towards normal, so that's why it's going to do light ray B. Good, so it's going to bend towards that normal. Okay, once we hit this side though, what do we do now? Hopefully you're thinking, now I have to draw another normal that is at 90 degrees to my boundary. And I think now, how do I draw the ray coming out? So you tell me, is it going to be option A? Is it going to be option B? Or is it going to be option C? Which one is it? A, B, or C? So remember what's happening, it goes from water to air. We know that it's going to speed up. It's going to bend away from the normal. So there's what would happen if it was to keep going straight through. So if it was to keep going straight through, it would go this way. So hopefully everyone realizes it's actually not good. We know it's not C. It has to bend away from the normal, but it's not A. Does anyone know why? Why is it not A? Why does it have to be B? Why does it have to be B and not A? How do we know? What are we looking for? Yeah, thank you. Good about people in parallel. That ray, and they look for this in your exam, this arrow and this arrow, they have to be parallel to each other. Okay, they have to be parallel to each other. So remember, that's what parallel lines are. Okay, so just make sure they're parallel to each other or they'll take the marks off. They have to be parallel. Good. Okay, what is the name of my dashed vertical line? So probably about 20 more minutes for combined. What is the name of that dashed vertical line? Yeah, beautiful. It's called the normal. Nice. Yeah. Yeah, nice, Callum. Nice, Jasmine. Good. Which angle is the angle of refraction? Which angle is the angle of refraction? Oh, very good. Oh, we're between V and W. We'll do a poll. We'll do a poll. Okay, is it V or is it W? That's what we're between. Which angle is the angle of refraction? Okay, and in 5, 4, 3, 2. Oh, we're not sure. Yeah, 63% were right. Oops. 63% were right. Yeah, it's going to be V. Okay. V is the angle of refraction. It's between, that's why we draw the normal in the first place. It's always between the normal and the ray. So there, between the ray and the normal, that's my angle of incidence between my incoming ray and the normal. And then my angle of refraction is between the ray and the normal, right? That's the whole reason we draw the normal. Good. Yeah, Y was our angle of incidence. Okay, why does refraction occur in the first place? None of the above. Why does refraction occur in the first place? It's nothing. W is nothing. Z is nothing. Good. Yeah, Pippa. Because it enters mediums or materials of different densities. So what does it do when it enters somewhere of a different density? What happens to the light ray if it enters somewhere of a different density? What does it change? What's the next part of that sentence? Yeah, good. It's going to, yeah, good. It's going to, well, we don't know if it's going to slow down or speed up. We're just going to say it's going to change speed. Okay, so that's why it changes direction. So refraction occurs when light rays enter different densities. What happens is they're going to change speed. Okay, good. They're going to change speed. Yeah, good, good, Tyranny. Yeah, good. Very good. Okay, you're happy. No, we're on the last bit of our topic now. So hopefully 15 minutes and we'll be done with combined. Okay, first question. What is my rule? What is the rule? How do we know what is going to attract and what's going to repel? We love magnets. Yes, good, Krish. Think about love life, right? We know that opposites attract, right? Opposites attract. Good. And we know that likes repel. So these are going to repel. These are going to repel. These are going to attract. And these are going to attract, right? Because they're opposites. Opposites attract. And the ones that are like facing each other repel. Good. Which ones are going to feel the strongest force of attraction and why? Which one feels the strongest force of attraction and why? Imogen, good. Why? Nope, Zane, number one's going to repel. Tara, one repels. Which one's the strongest attraction? Charlotte, good. It's going to be number 4 because they are the closest together. Nice. The closer they are together, they're stronger the force of attraction. Nice. Okay, in the objects below, in the options below, which ones are magnetic? Which ones are magnetic? Which ones are magnetic? Okay, legend, good. Steel is one that is magnetic. Nice. Philip, iron is another one that is magnetic. Yes. Cobalt. Oh, careful, Jasmine. Good. Cobalt, perfection, good. Cobalt, nice. And cash play, good. And nickel, good. The rest of them are not magnetic, okay? Remember, they always put copper in there to trick you. Be careful about copper. They always try to trick you with copper, right? They always try to trick you. You need to know that these are the 4 magnetic materials. The 4 magnetic materials. Which one is the one that is only a permanent magnet? Which is the one that is a permanent magnet? Which one is the permanent magnet? Oh, we don't know. No, no, no. It's too many irons. It's not iron. Steel is the permanent. Steel is the permanent magnet. It's the only one that is always magnetic, right? So all of these are made of steel because they're always magnetic, right? They're always magnetic because they're all made of steel, okay? What do we call iron, nickel, and cobalt then? What is iron, nickel, and cobalt? What type of magnets are they? They're not permanent magnets. What are they? Good, Maka, good. They are induced magnets. What is an induced magnet? What does that even mean? What is an induced magnet? What does that mean? What does an induced magnet mean? They can, yeah, they're right, good, right. They only become magnetic. And what's the rule about them? If in a magnetic field. So what that means is if you have like a little bag of iron nails, right? Maybe you're helping your dad outside or your brother or something, right? If you got a bag of iron nails, right? They're not all stuck together. They're all loose. They're all shaking there. Okay. They're not magnetic. But if I put them near my permanent magnet, my steel, what's going to happen is they're all going to become magnetic. And if they all become magnetic, good job, Moon, beautiful. They're always going to get attracted. Okay. So that's what happens. So the rule is that they are always, and you've got to remember that, and everyone forgets it when they start to do exam questions, they are always attracted. Okay, always attracted. Never repelled, always attracted. Okay? Okay, if I want to draw magnetic field lines around this, how would I do it? I would draw magnetic field lines around this. Ask Santa. Good. Good. Mohammed, nice. Yeah, good. So if anyone's not in my full course or not seen my TikToks, how I remember it is Santa Claus lives in the North Pole. Santa Claus has to come out of the North Pole to deliver his presents. He has to come out of the North Pole and go around the world. So out of the North Pole and go around the world, out of the North Pole and around the world to deliver his presents. That means he has to go into the South Pole. Okay? So Santa Claus has lived in the North Pole and it's go out of the North Pole to deliver his presents. It's go around the world to deliver his presents. Megan, just the magnet. Okay, where is the magnetic field the strongest? Where is it strongest? Sky, they never repel. They're always attracted. Good, good, good. How do we know it's strongest at the poles? Good. How do we know? What do you see? How do we know it's strongest at the poles? So the North Pole, the South Pole. Ria, I'm glad it helps. Good, because there's the field lines, nice. The field lines are closer together, right? The field lines are closer together, or you could say they're more dense. So where the field lines are closer together or more dense, that's where you know it's the strongest. Good. Good. Very good. Okay, next one. What about an electromagnet? An electromagnet is when we can use electricity to make something magnetic. Okay, so it's not magnetic by itself. It only becomes magnetic if we use electricity. So what we can do is that I can have a battery or a cell. We can connect it to a wire. And what we can do is we can make an electromagnet. Okay, so we can make the wire become magnetic. So what would happen if instead of having the wire flat, we wrapped it in a coil? So if we wrapped it in a coil, what's going to happen? Good, good, Mohammed, right? We're going to increase the strength of the magnet, right? We're going to increase the strength of the magnet. Yeah, nice, very good. So what we do, what we just said, one way to make it stronger is instead of having that wire flat, what I can do is just wrap the wire in a coil, because what I've got is more length of wire now, right? I've got more wire packed into a short space. I've increased the length of that wire by wrapping more coils. And something you know about is just a solenoid just means when you wrap the wire in a coil. So if I take my wire and I wrap it up in a coil, that's just what we call a solenoid, okay? Why can we put an iron core in the middle? What do you think the iron core does? Yeah, Khalid, not really D, but the opposite one. Yeah, right. Iron can be easily magnetized. Why can it be easily magnetized? What do you know about iron? Yeah, thank you, Polito. Good. Easily magnetized because iron is an induced magnet. So remember, what we said here is that we already have a magnetic field around this wire, right? We already have a magnetic field around this wire. So we do have a magnetic field around this wire already. We have a magnetic field around this wire already, right? Bear with. We have a magnetic field around this wire already, okay? So we have a magnetic field around the wires already. So if I put my just magnet inside it, if I put my iron inside it, because it's in a magnetic field, it now becomes magnetic. So if it becomes magnetic, it's going to make the whole thing a stronger magnet. Good. It's going to make the whole thing a stronger magnet. Okay, what happens if we increase the current? Yeah, the live is saved. You can watch it again anytime you want to. Yeah. What happens if we increase the current? Good. Good job. The magnetic field is stronger. Okay, and one way we can increase the current is just by adding more of those cells or adding more of those batteries. Good, very good. So we use electricity to make a magnet. Perfect. Okay, to see if we were listening, we'll do a poll. Is the answer A, is it B, or is it C? Go. Is it A, B, or C? What is a solenoid? Do it in the poll. What does the word solenoid even mean? Okay, 5, 4, 3, 2, 1. Beautiful. Easy. Yes. Good. 92%. 92% know that a solenoid just means a coiled wire. It just means we take a piece of wire and we wrap it in a coil. Beautiful. Easy. Right. Next one. We'll do a poll again. Is the answer A? Is it B? or is it C? Go. What are electromagnets? Okay, 5 seconds. 4 seconds. 3 seconds. 2 seconds. And 1 second. Oh, not as confident this one, but most of us are good. Good. Electromagnets need electricity to work, right? 82%. Electromagnets, they're only magnetic if we have electricity. They're not bar magnets. Bar magnets are those things made of steel. They're not permanent magnets. Again, that's those things made of steel. Okay. Fleming's left-hand rule. Next bit. Okay, Fleming's left-hand rule is only for higher tier. So Fleming's left-hand rule, we need to know that Fleming's left-hand rule, we can use his left hand, so my left hand, to figure out the direction of a force on a wire. Okay, stay with me. So it says force, put our hands up, your thumb goes up as like you're pointing the thumbs up at someone. Your first finger goes out like a gun, and your second finger goes out at right angles to the first. Okay, remember, you just lock your fingers and you move your elbow to move things around. So we use bil to help us out because what it says is F equals BIL. So the first thing is your thumb is the force. Your second thing is magnetic field. That's your second finger. And your next finger, your second finger, is your current. So thumb is your force. Your first finger, we could say your index finger, is your magnetic field. And your second finger is going to be that direction of the current. Okay. You need to know what B is. B is magnetic flux, and it's always measured in Teslas. It basically just tells you how strong the magnet is. Okay, so which is it's got a stronger magnetic flux, A or B? ZY, yes you do. So the right hand tells you the direction of the current in the wire. We'll talk about that in 2 seconds. Good, right? Clearly A has a stronger magnetic flux. We can see that because we see there's more magnetic field lines. The magnetic field lines are much closer together. So it's going to have a higher value of that Teslas. Remember, Teslas is like the Tesla car. Okay. I represents current. Okay. So current, remember, has to always go from the longer positive side round to the negative side. So remember, it has to go out of positive and it always goes round towards that negative. Okay. Someone asked there, what's the right hand rule? The right hand rule is when you use your thumb to show you the direction of the current. So if the current's going up, and your fingers coil in the direction of the current. So the coil here is coming towards my face. So that's just showing us the direction of that magnetic field around a wire. So you use your right hand with your thumb pointing upwards, and your fingers are curling round to show you the direction of that magnetic field. And your left hand, Fleming's left hand rule, shows you the direction of the force on the wire. At the end, magnetic field's always better. Okay. Okay, someone tell me, what is going to be my force in this picture? What direction is the force in this picture? What direction is the force in this picture? Your options are going to be out of page. Is it going to be into page? Is it going to be right? Is it going to be left? Or is it going to be up? Or is it going to be down? I'm seeing up and I'm seeing out of page. So we're between up and we're between out of page. Okay, so remember what you do is take your left hand, my left hand. So remember, mine's going to be a mirror image. So you've got to do it like the opposite way to me. So I do my left hand. Now what I've got is my magnetic field is always going from north to south. So remember, it's F, B, I. So this is my magnetic field. Has to be going from north to south. So pointing towards my right. My current is going down, right? So I need to move my current finger to point down. So my current finger should be pointing down. So what should happen is your thumb should be pointing at your face. Okay, so it's pointing at your face, is coming out of the board or out of the page. So that's why it's going to be out of the page. Yeah, towards you. Good. This stuff is always 1 mark, so don't be stressing if you can't do it right now. It's not the most important stuff. But yeah, it's going to be, yeah, out of page, Gwen, or out of paper. Yeah, out. Okay, this one. What is the direction of the force in the image? Is it up, down, left, right, out of page, or into page? Yes, you can, Lucia. Yes, it is SAI. Okay, I'm seeing outs, I'm seeing ups. Okay, I'm seeing a lot of outs and I'm seeing a lot of ups. Okay, current again. Remember, current's conventional current. It has to go out of the positive. So always comes out that longer side. Just remember longer side, always out of the longer side. And then we follow it through to see what direction it's going in to that current side. So if I look here, that current is going down. I know magnetic fields. Santa Claus lives in the North Pole. He has come out of the North Pole to go around the world. So magnetic field's going this way. So I use my left hand. I have to make sure that, remember, it's F, B, I have to make sure my magnetic field is pointing towards my right. So my magnetic field is pointing towards my right. My current, again, is going to be pointing down. So I move my current finger to point down. And again, my thumb, or your thumb, should be pointing towards your face. So if it's pointing towards your face, again, it's coming out of the page. Out of the page. Yeah? Right. Last thing, and then we're done with combined. We didn't do too bad. Last thing, okay? Again, Sophie, you can watch it again, and we just need to watch it. And remember, it's a mirror image here. So when I do my hand, remember, it's the opposite way around your hand will be. So that's why I say point your finger to the right, or point your hand up, your finger down. Yeah. Current, Peter, we said, goes out of positive and around to negative. Always out of the longer side of the cell, round towards the shorter side of the cell. Out the longer side of the battery, and work to the shorter side of the battery. Yes, EC, because I drank my juice way too quick, so I have to go to the bathroom as well. Okay. Motor effect. Motor effect. Let's be pros. It says I've got my batteries, my cells. Remember, it comes out of positive and it goes round towards that negative. Okay, so first thing, if we have current in the wires, what do we have? Anytime I've got current in wires, what do I get? In the right hand rule, your thumb is the direction of the current. And your fingers are the direction of the magnetic field line. So current in wires, yeah, beautiful. We're going to get, yeah, Jasmine, we're going to get a magnetic field. Good. So anytime we have current in wires, we're going to get a magnetic field. So what we do is we have a magnetic field in these wires. Okay, so we have a magnetic field in these wires. Okay, so what happens? Why does it start spinning? Why does it start rotating? Why does it start spinning? Good, Mohammed. Very good. Current flows through the circuit, and the magnetic field lines of the coil cut the magnetic field lines of the magnet, causing forces, making it rotate. Every half turn, the split ring commutator brushes the force in the same direction. What do you mean brushes the force in the same direction? Just that last bit's a wee bit weird. Nope, this is not foundation. Sorry, this little slide's just higher tier. So what you should be saying is, I have a wire right now with a magnetic field lines around it. And I have a permanent magnet here with magnetic field lines. So what I'm getting is magnetic field lines that are crossing. So because the magnetic field lines from the wire cross the magnetic field lines of the permanent magnet, yes, Lily, we're going to get a force. Good. Good. Okay, why is the force on one side in a different direction from the other? Why is the force on one side different from the direction on the other? Good, Justin, right? The different forces because that the current there is going in different directions. The current here is going down, but the current on this side is going up. So as the current is flowing in different directions, the force is in opposite directions. Right? And we can prove that due to Fleming's left hand rule. Okay? So what happens is this side is going to go up and that side is going to go down. But what happens is when it flips over, it's just going to go back and forth, back and forth, back and forth, right? But I don't want it to go back and forth. I want it to do a whole motor. I want it to spin the whole way round. So why do we have this? How do we stop it just going back, forth, back, forth? How do we get to spin the whole way round? How do we get to spin the whole way round? Good. The split ring commutator. So the split is always got one mark at the end. The split ring commutator. Good. Very good, Justin. Yeah. Good, Bliff. Yeah, the split ring commutator switches the current every half turn to get or to allow a full rotation. So it does. See here? It switches that current every half turn to allow it to flip the whole way around. Okay? Try to flip the whole way around. Zayn, your right hand is for if I've got current in the wire, it shows me the direction of the magnetic field lines. Your left hand is to show you the direction of force. So I've got magnetic field going from north to south. Current here is going in this direction. So that's why then that my force is going to end up going up. Whereas on the other side, the current is going in this direction. So I have to switch my hand. So that's why I get force going down in this direction. Yeah, nice. It like lets it, see, when it, see how it flips around? When this flips around, that's my positive and that's my negative. It just flips around. Yeah, it just flips around. Guys, that was an intense course. We did it 2 hours and like 10 minutes because we had a wee bit of a break. This here is for you guys. It's a free revision course. If you did the Easter revision course, you already have it. If you didn't do the Easter revision course, scan the code and we will email you some past papers and some mark schemes for you to have a go at, okay? But remember, it's only paper 2 that you want to do, okay? So paper 2 stuff that you want to do. You guys have been awesome, okay? Again, absolutely awesome. It'd be lovely if you could leave us a review on Trustpilot, like so lovely. There's a link in the description and you'll get an email for it. And guys, I wish you all the best. You guys will do so well. Please, you have, look, it's only 6 o'clock. I know some of you say you got 2 exams tomorrow. That's triple. You only got 2 exams tomorrow. So just make sure that you spend a bit of time now, get something to eat with your family, take a break, and then just make sure you look over past paper questions. Okay. So yeah, triple is still to come. Caitlin, triple still to come. So this is just combined. People are free to go now. But you should be so proud of yourselves. That was our intense physics. Like we went through so much there. So yeah, we're still doing triple. We're still doing triple. So it's only combined people that I'm saying goodbye to right now, okay? And please remember, this video is saved, okay? So even though it's not over right now, you can just rewind it and go back to the start and do it again. When the lesson ends, again, you can rewind it and back to the start. Tomorrow morning, if you want to watch that little bit about motors right before exam, you can just rewind, you can just skip right to the end and watch that little bit right before exam, okay? So good luck tomorrow. Make sure you eat a good dinner. Make sure you get a good night's sleep. And let me know after how it went. And I hope you do well. Okay? Hope you do well. Yeah, good luck, guys. Good luck, good luck, good luck. Triple, I'm not gonna lie, I am dying for the loo because I just downed my water. So we're gonna have a quick break before we start triple. So triple, we will be done at 7 p.m. So triple, that's the goal, right? But it might be 7:15. Let's be real. Probably will be 7:15. So we're just gonna have a quick 5-minute break. So 8:25. 8:25, sorry, 6:25. That's not a quick break. Okay, 6:25, just 5 minutes, run to the bathroom, get a drink, and then we're going again. Okay, 5 minutos. I see you in 5 minutes. 5 minutes, 5 minutes, 5 minutes. Yes? Yeah, just triple, just triple. Okay, 5 minutes, guys. Good job, good job, good job. I need to run to the loo. Good job. Hi, bye-bye. Oh, wait, come on. Come here. Come here. Come here. Come say. Come say. Come. He's came to say hello to the triple lot. Say hi. Say hi. Tell him where you went today. Come here. They can't see you. Come here. Come closer. Up. Where'd you go today? You went to Clapham Park. No, don't spill that. Ah. Went to the park today. He had a big run. Had a big run yesterday, didn't she? Yeah. They terrorized some little man. They terrorized a little man that was out running. But he was fine, wasn't he? Wasn't he? But he was good. Yeah, right. Bye. JC, you saw me in the park. No, you did not. What park are you at? Also, why are you at the park? You've got exam tomorrow. Okay, are we ready for triple? Let's go. Last 40 minutes, guys. Do we think we have it? Last 40 minutes, yes. Okay, what is up first? No chicken. We've got this. What's up first? What's up first? Pressure increases because the height of the column increases. Which, keep going with that. A wee bit more than that, Abby. Up thrust is a force that is experienced by an object in a fluid due to particles in the fluid colliding with the object. They do, but particles are colliding with all parts of it. So why is there up thrust? Yeah, they're up thrust and upward force. It's a resultant force going upwards, but why? Look at my picture. Good, Jamaf, good. Look down here. Do you see here? Look at those arrows. What I'm trying to show you is there's different forces. There is a larger force on the bottom than on the top. Good. And there's a larger force, I know, good, because there's a greater pressure on the bottom. Why is there greater pressure on the bottom? How do we relate pressure and force? How do we relate pressure and force? Good, right? We're thinking pressure is equal to force divided by area, right? So what we're saying is yeah, good job, Mano. On this little unit area, there's a larger pressure. Because there's a larger pressure, there's a larger force. Yeah, Polito, good. The reason why is, think about water, right? So think about, I've got all these, imagine these are all my water molecules in there, right? They're in an irregular arrangement and they're all touching. So look here. Here, look how many water molecules are on top of this little unit, right? Pushing down on it. Whereas down here, there's loads more water molecules, right? There's loads more water molecules pushing down on it. So there's much larger pressure at the bottom, okay? So up thrust is a resultant force upwards in water because there's a larger force at the bottom, because there's a greater pressure at the bottom. Good. Okay, we just said this, so hopefully everyone gets this right. Does pressure increase or decrease with depth in the ocean? What do you think? As you go down further and further in the ocean, does the pressure get higher or lower? Yeah, beautiful. We just said this, right? The pressure increases because, like we said, there's a lot more water molecules that are all pushing down on top of you, okay? So there's more water molecules pushing down on you. There's a bigger force pushing down on you, so there's a bigger pressure. Good. Good. That's why you can't dive very deep in the ocean, because if you get too deep, your whole body would crush in on itself because the pressure outside would be so large. That's why when you want to go really deep in the ocean, yeah, we need to be in things like you said there, like submarines, Minato. Yeah, good. Okay, what about if I wanted to hike up a mountain? So let's say I start to hike up a mountain. What's going to happen to the pressure as I go up the mountain? Yeah, good. It's the opposite, right? Pressure decreases as you go up the mountain. Why does pressure decrease as you go up the mountain? So why does the pressure decrease as I go up the mountain? Good, right? There's less particles. So down here, maybe where your houses are or where you live, there's loads of air particles, right? There's loads of oxygen, there's loads of carbon dioxide, so we can breathe and we can live our lives. But as we go further up, there's less and less oxygen particles. So you can see what happens here. There's less particles. There's less dense. The air is less dense. So because the air is less dense, there's less particles, there's going to be less collisions, right? Less pressure. Another thing is, because there's less particles, there's also less particles above you. So if I was here, above me, there's barely any particles pushing down on me. But if I was live down here, there is loads of particles pushing down on me. So there's a larger weight pushing down on me. So again, what we can say is there's more dense particles and there's less particles above you. That's why if you go up a mountain, you probably have to take maybe an oxygen tank with you if you went up Mount Everest. Yeah, that's why it's hard to breathe, Amar. Good, because there's less particles up there. There's less oxygen for you to get into your body. Yeah, good. Okay, calculate the depth of a fish in the Dead Sea if it's experienced 15,500 pascals. This is the density, and this is what we're going to use for G. How do we do this? What is the equation we use for triple? What is the equation we use for triple? Yeah, generous. Yes, good, Abdullah. Pressure is equal to rho GH. The pressure is equal to the density times gravity times the height. The pressure is this thing in pascals, okay? Just so you remember, pressure is equal to force divided by area is equal to a Newton divided by a meter squared. So it's a Newton per meter squared. Or you can say pascals. You can say either one. The same way work done is Newton meters or it's joules. Pressure can be newtons per meter squared or pascals. Yeah, it's on your equation sheet for triple. It's on your equation sheet for triple. So that equation sheet I shared earlier, that was the combined one. So it's on your equation sheet for triple. So I do 15,500 is equal to the density, which is 1235, times G, which is 9.81, times by the height. Yeah, good guys. So we're getting 1.2 or 3. So what I would do first in my calculator is I would do 1235 times 9.8. Is it 9.8 or 9.81? Sorry, it's 9.8. It gives me 12103. So 12103 times the height is equal to 15500. So when I get the height by itself, we do the opposite of multiplying. The opposite of multiplying is divided. So I'm going to do what I do one side, I do the other. So in our calculators, we're going to do 15500 divided by the answer, and we get a height of 1.28. So perfect. Good. 1.28 meters. Nice. Good, Imogen. Nice. Good, Angie. Yeah. Good. Good, good, good. Lovely. Right, next one. So some of you asked me this about earlier. What's induced potential? Explain why the reading on the voltmeter changes when the magnet gets pushed into the coil of wire. So what would you write here to get all your marks? Might be like 4 marks or 3 marks. The last question was triple. So why would the reading on the voltmeter change as the magnet gets pushed in? Yeah, this is the generator effect. It is. So what's happening? Good, good. We're going to say, that's nice, Sam. We're going to say the magnetic field of the bar magnet cuts, well, no, it doesn't cut the magnetic field of there is no magnetic field in the coil. You only have a magnetic field in the coil. Be careful. You only have magnetic field in the coil if there's current in the coil. There's no current in the coil. The magnetic field line and the bar line cuts the coil. Is that okay? Please remember, there's no magnetic field right now in this coil. The only way that you get magnetic field in a coil of wire is if it was connected to a cell or battery. So if I have current through my coil, then I have a magnetic field. But there is no magnetic field right now. Right now, I only have my permanent magnet, my magnetic field lines of my permanent magnet. They're going to cut the coil. Yeah, GT. There's a change in my field. And what's that going to cause in the coil? What happens in the coil? So then in the coil, Chris will talk about it in 2 seconds. In the coil, what's going to happen? Handwriting. It says magnetic field, the bar magnet cuts the coil. See, coil. In the coil, thank you, Ayush. We have to say a potential difference is induced, right? It's really important that you say a potential difference is induced. If you don't say that, you're going to lose a mark. Potential difference is induced. Okay. What's the next line? A potential difference is induced. No, that's higher. Nope, you can't say current's induced. You're not going to mark. But you can say there is a current if there's a current if what? Yeah, perfection, good. The current if the circuit is complete. Right? And we can see here, this is a complete circuit. There's no gaps on it. So we're going to get a current through those wires. Good job. So that's why we get a reading on this voltmeter. Okay, so that's why we're going to get a reading on this voltmeter because it says there's a current in the wire. Yes, star. Okay. Okay, someone then asked, what is Lenz's law? Okay, the next bit that wasn't part of my question because the exam question just asked you why does the voltmeter changed. There's just extra stuff now. Now that I have a current in the wire, what's going to happen? So now we have a current in the wire. What is created around the wire? So now that we have current in the wire, because we just said we have current in the wire. So now that we have current in the wire, what happens? Good. Yes, Tyrena, good. Now we have current in the wire. Now the wire is going to have a magnetic field. Good. Remember we said anytime you've got current in the wire, we get a magnetic field. So now we have current in the wire, we get a magnetic field. Okay, what do you know about the magnetic field? So let's say that was a north pole of my magnet and that's a south pole. What is going to happen to this side of the coil? This is GCSE. What is going to happen to this side of the coil? This is GCSE triple higher. You don't need to know the name Lenz's law, but you need to know how it works. So one more time. So okay, don't stress. You don't need to know the name Lenz's law. Some people just put it in the chat because their teacher mentioned to them it's called Lenz's law. You don't need to know the name, but you do need to know the part in green. So now that we've got current for the magnet, current for our coil, we're going to get a magnetic field. Good, Crikey, good. And it's going to cause a north pole on the right side to repel or to oppose the incoming north side. Okay, so that's what it's called, Lenz's law. You don't need to know the word Lenz's law, but you do need to know the part in green. So again, what we just said is if the magnet goes into the coil, because I've got magnetic field lines cut in the coil, I'm going to get a potential difference in just, and that line is so important. And then if it's a complete circuit, we get a current. Okay. Now I've got current in the coil, so because it's complete circuit and I've got current in my coil, now I have a magnetic field lines around my coil. The magnetic field around my coil is going to oppose the change that causes it. So if a north pole got pushed in order to oppose it, that's going to become a north pole. To try and stop that north pole coming in, it's going to try and repel it. Remember, at the end, if we have time, we can. Okay, space. Okay, this one's going to be a bit of me talking, and then we're going to ask you questions after, okay? So this one's just me talking, and we'll do questions after. No, Fisprim, you've missed it. The magnetic field cuts the coil, and that gives us a potential difference. And if it's a complete circuit, that's how we got the current. So because we pushed a magnet in, that's how we got a current. Now we have the current, now we know there's a magnetic field. Yeah? Okay. Things you need to know. So it's going to be a bit me talking. A lot of people mention transformers. We can do it at the end if we have time. Okay, so this one says, the sun is a star. The star has 8 planets orbiting it. Why is it not 9? What happened? Tell me, what happened to Pluto? Because you need to know what it is. What is Pluto? Why is there only 8 planets orbiting our sun? And why not 9? Yeah, good. Thank you. Because Pluto is now too small, so we call it a dwarf planet. The moon orbits the Earth. What do we call the moon if it orbits the Earth? So planets orbit the sun. They orbit stars. Moons, good job, are satellites. Good job, Shantids. They're satellites. They're satellites because they orbit planets. Good job. So let's say here's my planet Earth, and let's say I've got the moon orbiting the Earth. What causes the moon to orbit the Earth? What did we just say? What have I got there? It's written there. What causes the moon to orbit the Earth? Gravity, thank you. The force of gravity is going to pull the moon towards the Earth. Good job. Okay, what do you know about the speed of the moon and what do you know about the velocity of the moon? What do you know about the speed of the moon and what do you know about the velocity of the moon? Good, Plato, good. The speed is constant. The speed of the moon is not changing. The speed of the moon is not changing, but its velocity changes. Good job. The velocity changes because it is a vector and the direction is changing. The direction of motion is changing. Good. Because we look here, there it's going in this direction. If we look here, it's going in this direction. If I look here, it's going in this direction. So because the direction that is constantly changing, its velocity is constantly changing, even though its speed stays the same. Good. Good. Okay, next one. You need to know about how stars are formed. Okay, so I'm going to talk. Please make notes while I'm talking, okay? So it says, there is a force of cloud of gas and dust. So at the beginning, there's just a cloud of gas and dust. Okay, what's going to happen is we know gravity pulls things of mass together. So gravity is going to pull all of this cloud of gas and dust together. And then what happens is that the temperature is going to increase, right? Because we're going to increase that thermal energy. So we start pulling them all together, we're going to increase the thermal energy. And what's going to happen, eventually we're going to get to a certain temperature where, what do you think, fusion or fission? Yeah, good, Mohammed, where fusion can happen. And what fusion is when we have two light nuclei that join together to make one heavier nucleus. Okay, that's what fusion is. So I might have something like two light hydrogen nuclei that join together to make a heavier helium nucleus. Okay, so fusion is we join two light nuclei together to make a heavier nucleus. Okay, as soon as fusion happens, it becomes a main sequence star. A main sequence star is currently what our sun is. Okay, main sequence star is currently what our sun is. Okay, guys, I can see all your questions. I know a lot of you asked about transformers. A lot of you are asking about the Doppler effect and extra things. But if you're reading your questions right now, I can't describe the diagram. And if I'm reading your questions, you're not making notes. So please, please, please make notes because you're going to miss your questions. So what's going to happen then is the main sequence star is our sun. Our sun is currently doing fusion. Okay. What happens is at the end of the life cycle of our sun, because our sun has got a low mass, right? It's got a low mass. Because it has a low mass, what's going to happen is it's going to form a red giant. Okay? So it forms a red giant. So that means that it swells slightly and it forms a red giant. After it swells slightly, what's going to happen is some of those layers just pass off. They just pass off into space. And then it forms a white dwarf. Okay, it's called a dwarf because it's much smaller. That white dwarf is going to cool down over time, and that's why then it's going to form a black dwarf. Okay, so that's what our sun is going to do because it's low mass. Anything that is heavier than the sun, so things that are heavier than the sun, what happens is they're going to form red supergiants. Okay, it's much bigger. Red supergiants. Those red supergiants, they have so much energy. What happens is they're going to collapse in themselves and then they rebound out and it forms this big explosion. And this big explosion is called a supernova. So that's our big explosion. And then what gets left behind after that explosion is going to be a neutron star. And it just means that it's made of neutrons. The only thing inside it is neutrons. So a neutron star is made of neutrons. Or it forms a black hole. And a black hole is black because it doesn't emit any light. We can't see it. Okay? The other thing you need to know is that the heaviest thing that can be made inside a star is iron. Okay, so iron is the heaviest thing that can be made inside a star. Any elements that are heavier than iron get made in the supernova in that explosion. Okay, so things like uranium that are really big, uranium-235, they don't get made in fusion in the star, they get made in the supernova. Okay. Yeah, iron is made in the main sequence star, Jazz. Yeah, it's the heaviest element that could be made by fusion in stars. Anything heavier than that has to be made in supernovas. Yeah, good. Okay, it depends on the size of the star, whether it forms a neutron star or a black hole. Okay, next thing you know about, and then ask questions. Next thing you know about is one thing we do on Earth. So there's my planet Earth. We have telescopes all over the planet Earth. And what we do is we observe all of these stars around planet Earth. And what we observed is that most of the stars are moving away from us. Most of the stars are moving away from us. So what that means is if they're moving away from us, the light has a bigger distance to travel before it reaches us. So because the light has a bigger distance to travel before it reaches us, it gets shifted towards the red end of the spectrum, okay? And that's why we call it red shift. It doesn't mean the light is red. It just means it's shifted towards the red end of the spectrum, okay? So let's say you had, I don't know, some type of spectrum. There's my spectrum before. And then here's my spectrum after. Let's say this here is my long wavelength, and here's my short wavelength. If it is red shifted, these are going to get shifted towards the longer end. It doesn't mean it's red light. It gets shifted towards the longer end of the spectrum, okay? If by some reason there's some star, there's very, very few, but there is some of them might be moving towards us. If they're moving towards us, that light has a shorter distance to travel before it reaches us. So that's why we call it blue shift. So blue shift is something moving towards us, and red shift, yeah, Vesprin, good job, Andromeda Galaxy. So blue shift is something moving towards us, and red shift is something moving away from us, okay? There is a problem because what we saw is that when we looked at really, really far away supernova, they're actually too redshifted. They're too far away. They're traveling too fast. So what we're thinking is, what caused that? Where did that energy come from? And that's when we started to think it might be because of dark energy. Okay, so again, stars we know are redshifted because they're moving away from us. All stars are moving away from us because the universe is expanding. That makes sense, right? The stars are moving away from us because the universe is expanding. The further away the star is, the more the light is redshifted, the faster it's moving away from us. But when we looked at these really distant supernova, those explosions, we saw that they're too redshifted. Because they're too redshifted, that means they're too far away, they're traveling too fast. So there it means some energy had caused that. We're trying to think, where did that energy come from? And we don't know right now. And that's why we think it's caused by dark energy. Okay? Okay. To practice. Multiple choice. Remember, you guys, you can watch it back anytime you need to. What is the correct answer? Right? What does redshift tell us about the universe? 5, 4, 3, 2, 1. Good. Easy, right? Redshift tells us the universe is expanding. Because again, what we said was, I've got the planet Earth, and I've got these telescopes on planet Earth, and what we're doing is we're looking at all the stars. And when we look at the stars, most of the stars are moving away from us. And if they're moving away from us, it tells us the universe is expanding. This light has further to travel, so it gets shifted towards that red end of the spectrum. Good. Very good. We don't know what dark energy, Mark, is. It's just a guess to think why are they all traveling away from us? Okay. One thing I didn't mention was this tells us, redshift tells us the universe is expanding. How do we think the universe began? Why is it expanding? How do we think it began? Yes, JJ World. So why is the universe expanding? How do we think it began? Good. We think it began an explosion. We think it began in the Big Bang. The Big Bang is an explosion. That makes sense. A small hot region that then exploded outwards, and that's why everything is moving away from each other. Good job. So one evidence for the Big Bang is this redshift. It shows that the universe is expanding. What other evidence is there to support the Big Bang? What other evidence is there to support the Big Bang? Yeah, good job, Bertie. Nice. The cosmic microwave background radiation. So the cosmic microwave background radiation is radiation left over from explosion. It makes sense, right? An explosion is going to have radiation. So there's leftover radiation from this explosion. But because it was so long ago, all that radiation is shifted towards the longer end of the waves. So think about the waves. You've got radio waves, microwaves, infrared, micro, X-rays, and gamma. When that explosion first happened, all of that energy was probably really high energy gamma. But because it happened so long ago, the gamma rays, they spread out to longer and longer and longer wavelengths. And now that's why we say that they're microwave. So it's cosmic because they're in space, cosmic microwave background radiation. Yes, you do need to know that. Yes, you do. Okay, next thing you need to know about, and I didn't say this one, but I just wanted to make sure that, see if you know it, but you do need to know it. What is a geostationary satellite? Think about what the word geo means. I'm thinking about geography. Geography is to do with the Earth. Geography is to do with the Earth. Geo, think about the word stationary means. What does the word stationary mean? Okay, 5, 4, 3, 2, 1. Ooh, 41%. Good job. So a geostationary satellite is, remember we said a satellite is something that orbits a planet. So if I've got the Earth and I've got these satellites that are orbiting the Earth, geostationary, geo is orbiting the Earth. That's why it says geo there. And what we know is if I live here on Earth, if my house is there, if that satellite, it looks stationary. It looks like it's always right above me. So when the Earth rotates round, the satellite also moves round. So when the Earth rotates round, that I now live here, because the satellite also moved round, it looks like it's still above me. So that's why we say it's stationary. So a geostationary satellite, it orbits the Earth at the same time it takes the Earth to rotate. And we know it takes 24 hours for the Earth to rotate, or that's equal to 1 day. 1 day is time for the Earth to rotate, which is the time for that geostationary orbit to rotate. Someone wrote in the chat earlier about that force. Remember we said it's gravity pulling it together? That's called someone wrote it's called the centripetal force. It keeps it moving in a circle. Okay, centripetal force. DG, good. It's called centripetal force caused by gravity. Keeps it moving in a circle. Other satellites are like International Space Station, but they're artificial satellites, not natural satellites. Centrifugal is not a real force. Never use that word, Vanessa. Okay, next one. What is A? What is B? What is C? And what is D? Go. Okay, again, I saw some of you be in the chat, be like, oh, my teacher never taught me this. Oh, is this AQA? I promise this is AQA. This is the stuff you need to know. If your teacher didn't teach it, maybe you were sick a day. Maybe they forgot. But yeah, but that's okay, right? That you're here. This is a free lesson. Happy days, right? So hopefully it's helping you guys out. Okay, 5, 4, 3, Serena, a little bit. 2, 1. So cosmic microwave background radiation. Someone earlier asked what CMBR means. Cosmic microwave background radiation. Good job for the 89%. It supports the Big Bang theory, right? If there was a Big Bang, if there was an explosion, we think there was going to be, anytime there's an explosion or a bomb, there's radiation emitted, okay? And that radiation, yeah, exactly, Mohammed. That radiation was probably gamma, really high energy. Remember, gamma is that really short wavelength. But over time, because the universe expanded, that got shifted to longer and longer and longer wavelengths because it caused further and further to travel. And now it's shifted towards those longer wavelengths called the microwaves. Good. Yes, you can use abbreviation, Jess. Okay, moments. A child has a mass of 30 kilograms. You guys are triple, so hopefully you can just fly through this yourselves and pop your answers in the chat. It says a child of mass of 30 kilograms sits 2.5 meters from the pivot. It says another child sits aside 1.5 meters away. So I would do 1.5 meters and I would do 2.5 meters from my pivot. The pivot is just that little point on the seesaw. Okay. So I got one person says 50 kilograms. I got another person says 60. Okay, what it says is that the other person's got a mass of 30 kilograms. I want to know what's the mass of this person. That's what we're asking for. No, it doesn't. Sorry. It says what's the weight. I apologize. Ask what their weight is. Oh, well, 50 must be wrong because of the question. So 50 can't be right because it can't be kilograms. So Daniel says it's going to be 490. Okay, so yeah, moments. Moments tells us force times by distance, the perpendicular distance. So I know that moments in the clockwise direction must always equal moments in the anti-clockwise direction. So I know that 2.5 is the distance times the force. 30 kilograms is not a force. So I have to think, how can I get a mass into a force? I know W equals mg. So I do 30. I'm going to multiply by 9.8. And sorry, I should have given you that number. So I should have said use G. 30 times 9.8 is going to equal 1.5 times whatever that force is on the other side. So in your calculator, I would do 30 multiplied by 9.8, figure out what that weight is, what that force is, multiplied by the distance, which is 2.5, is that side, so 735. So I know that 735 has to equal 1.5 times by the other force. So to find what the other force is, I do the opposite of multiplying, which is divide. And what we do to one side, we have to do the other. So what we're doing here is 735 divided by 1.5, and we get, beautiful, good job, 490 newtons. Good. 490 newtons. Good, good, good. Good. Right, next one. Someone asked about lenses. So it says, a door is fitted with a security lens that is concave. Please make sure you always look to see what it is. How do I do this? Someone tell me, what is the image like? Yeah, put the units in. Normally the unit's on the answer line, but just always check it. Yeah, they're going to diverge. Good. Concave lens makes them diverge. It's really important that you remember that. Good. Remember, concave is the one that's thinner in the middle. So what they do is they make light rays diverge. They make them spread out. Good job. The other type of lens, just for revision, is called a concave lens. And we draw that one with the arrows pointing outwards to show that it's kind of like fatter in the middle. And the concave lens, they make the light rays converge. They make them come together. Yeah, good. So what we do is we draw a light ray going from the top of our object towards the lens. Oh, sorry. Yes, thank you. The other one is the convex lens. Thank you. That's fat in the middle, and then the light rays converge. So this one's our concave one. How do I draw this light ray now? That's the way it's going. What we do is that you go from you take a dotted line from the focal point to that point, and then you draw a solid line outwards. So that's the way that's going to diverge. So you take a dotted line from the focal point, you draw it up, it makes it diverge. The other one, remember, has to always go straight through the center of the lens. So this one always happens, no matter what type of lens it is. Okay, so then what we do is we look where they cross, and wherever they cross, that is my image. Okay, is my image virtual or real? Cube core, very good. Good, very good. Right, good. It is virtual because real light rays didn't cross. Yes, there's one light ray, but that is not a real light ray. That is just how we traced it back. This is the real light ray. So it's virtual because two real light rays didn't cross. It is upright because it's the same way up as the person, and it is diminished. That was nice, or smaller. So diminished or smaller. Very good. Very good. Very good. Very good. Do convex. So let's say you had a convex lens, and there's my two focal points. And there is my, I don't know, there's my object. Again, you do your ray parallel first, same as here. We do our ray parallel, same as before, but this time it goes through the focal point. So see here, we pretended it came from the focal point. This time it goes through the focal point. And then the other light ray is the same as this one. It just always goes through the center. And you just keep them going until they cross. And wherever they cross, that's where my image is going to be. And that image is inverted because it's upside down. That one is slightly larger, but not by much. So it's magnified. And it is a real image because the light rays actually crossed. Okay. This was a past paper question. If they don't cross, it's virtual. Okay, it says a security lock is fitted. Explain why the door unlocks when the switch is closed. So this is all one past paper question. The focal points tell us how strong the lens is, Polito. Toby, you're so welcome. Rashid, which one? Sorry. The security is fitted with a lock. Why does the door unlock when the switch is closed? What happens when I close that switch? Good, Rashid. Thank you. When we close the switch, there's going to be a current in the solenoid. What happens if I have current in my wires in my solenoid? Grace, wherever your image is. So see, the lines crossed there, so there. The lines crossed here, so here. What happens when we get current? Yeah, good, Natasha, good. The current in solenoid, we know we're going to get a magnetic field is formed in the solenoid or in the wire. So what's going to happen now? Yeah, good, Natasha, right? Now it's going to attract the bolt. Good. And if it attracts the bolt towards that solenoid, that's when my door is going to open. Yeah, beautiful. That was very good. Right, last question. When the door is opened, the spring extends by 1.5 centimeters when a force of 2.9 is applied. What is the spring constant? Can I say current flows for the wire inducing the bolt, iron bolt? What do you mean inducing the iron bolt? You have to say that there is a magnetic field, Mohammed, first, or why would the iron bolt even be induced? Good. It's centimeters. So first thing you're thinking is unit conversion. Divide by 100. Century is 100 years. So 0.0 divide by 10 divide by 100. 15 meters. Beautiful. Yep. F equals KE. So 2.9 is equal to K times by 0.015. Get K by itself. We do the opposite multiplying, which divide. What we do to one side, we do the other. What do we get? 100. Good. 193.3. Beautiful. And what we did was we did a force divided by an extension. We did a Newton divided by a meter. So that's why the unit then is Newton/meters. Rashid, you know, I actually figured out a lot of you would ask about transformers because you were asking about it in the chat. So yeah, if you want to stay for a bit longer, I did find a transformer question. No, I didn't. I found a demo question. So really quickly, we can do a quick one on transformers. And then we'll call it a day, okay? Transformers. What are transformers made of? What is transformers made of? Yeah, they're made of iron. Good job. They have an iron core. So what that means is it's just kind of like a solid brick with this like hole in the middle. So it's got this like hole in the middle, but it's an iron core. Good. Now what we do is we wrap wires around this arm. That's called the primary because it's the first arm. And then we wrap other wires around this arm, and that's the secondary because it is this secondary arm. Okay. Right now, looking at this one, did I draw a step up or did I draw a step down transformer? What did I draw? Just by looking at it, do we know? Did I draw a step up or did I draw a step down transformer? Good. I drew a step up transformer because there's more wires, there's more coils in a secondary arm. Okay? And there's an equation in your formula sheet. It says that VP over VS is equal to NP over NS. So we can see where the voltage is in that primary arm, so where the voltage in the primary arm, divided by the voltage in the secondary arm, is going to equal to the number of turns on my primary arm, divided by the number of turns on my secondary arm. Okay? Okay, next thing you need to know is why is it made of soft iron? Why should we say that it's made of soft iron? What's important about it being made of soft iron? This is AQA, yeah. Good job, Generous, because it's easily magnetized and demagnetized. Good, nice. Okay, what do you know about the current that goes in here? What do you know about the current that goes into the primary arm? What do you know about the current that goes into the primary arm? Isabel, if maybe I get time, I don't want to go over 7:15 because I want to give you time to like decompress. Good. It has to be alternating current. Remember, alternating current means it goes in both directions, right? Up and down. It goes left and right. So current goes forwards and backwards, right? It goes in both directions. So I have current that's constantly changing directions in this wire. What is created in this wire? If I've got current that's constantly changing directions, what do we get created in this wire? What do we get created in this wire? Good. We're going to get a magnetic field. Is the magnetic field going to be always in the same direction or different directions? Good. As ISUM, good. It's going to be a changing magnetic field. Because I current going one way, making magnetic field lines in one direction, then I current going the other way, making magnetic field lines in the other direction. So I'm getting magnetic field lines that are constantly changing direction inside this transformer. So now, if I look over here at my secondary arm, so I have magnetic field lines that are constantly changing direction. What's going to happen to this secondary arm? If I've got magnetic field lines that are constantly changing direction. Good, very good, Subhan. Yeah, good job. If we have a changing magnetic field, and it's going to cut the wire or cut the coil, we're going to get an induced potential difference. Remember, if it's a part of a complete circuit, we get a current. So I'm going to get an induced potential difference, but it's going to be alternating because the magnetic field is alternating. And that's why we then get voltage out on that secondary arm. Cut just means they pass for each other, or just pass for each other. Yeah, cut just means that they like cross. So cut could also be like cross. They pass for each other, across each other. Okay, this is going to be super quick, but what you need to know about P and S waves. Okay, if I was doing it, I think S waves, just because I got asked about in the chat, I think an S wave, I think of sound waves, right? But it's not a sound wave, so it's not actually nothing like a sound wave. I know a sound wave is a longitudinal wave, but it's not a sound wave. It's nothing like a sound wave, so it must be a transverse wave. So then a P wave is the longitudinal one. P waves are primary because they always travel fast and they always get there first. S waves are much slower. They always get there. That's a secondary wave because they get much slower. These are called seismic waves. They're called seismic waves because they normally come from earthquakes. Yeah. The P waves are the primary waves. They can travel much faster. They can go through solids and through liquids. But a secondary wave that's much slower can only travel through solids. So that's how we can figure out if there's a liquid in the earth, because if we can get the waves, if we can get P waves on the other side of the earth, we know that there is a liquid there. But if we can't get S waves, there must be a liquid there because the S wave can't get through. Tahir, because of this equation over here. Okay. Rashid, do a dynamo. This has to be the last suggestion we take. Okay, bear with. Okay, dynamo. A dynamo looks like the word DC, so dynamo is always direct. Okay, so it's always going to be direct current. So if you get asked about a dynamo, I have a wire here. What is the wire going to do? What is the wire going to do? What is the wire going to do? Yeah, thank you, Ella. So what we do is that a dynamo is kind of like a generator. We turn the wire, okay? So what we're going to do is we're going to turn the wire, or we're going to spin the wire or spin the coil. Okay, what happens then? If I just turn this wire, thank you, Renan, good. Look, I've got a magnetic field here from my permanent magnet. So it's going to cut, or you could say cross, the magnetic field from the permanent magnets. Okay, what has to be the next line? Good job, POTUS, but we can't say induced current. You don't get marks for saying induced current. Please, please, please remember that. You don't get marks for saying induced current. Yep, L. You have to say induced, or a potential difference is induced. Right, we get an induced potential difference. The next line, if it is a complete circuit, that's when we get a current. Okay, only if it's complete circuit. Okay, get complete circuit, that's when we get a current. Okay, if you want to do a graph of it, because it's always in one direction, it always goes like this. right? And it stays in that one direction because of this commutator. The commutator switches contacts every half turn to keep the current in one direction. Hannah, the generator effect, so just to make sure we're good, if I asked you about an alternator, and alternator is the same green lines are the exact same, those ones the same, except for the last bullet point. So an alternator would be like this. So an alternator, both of these, all of it is the generator effect. But a dynamo is DC, direct current, and alternator is AC, that alternating. Okay. The brushes are only in, so again, the brushes are only in the dynamo because what they do is they allow it to switch every half turn to keep the current in one direction. But you don't need that in an alternator because you want it to switch directions. Commutator or split ring commutator, either one artifact is fine. Yeah, either one is fine. Guys, we did even more than what you wanted. That's mad. And please, you did so well. Please remember there are other subjects if you need them. Maths, biology, English, but you're probably all done with most of them now, right? And remember, you can scan this if you need it, but it was for the Cram. If you're in the Cram course, you've already done it. So in the Cram course, if you're in the Easter Revision course, you've already done it, okay? Predictions, Alex, honestly, I would say it's hard to predict what comes up, I'm not going to lie, but the stuff I focus on today is the stuff that I think is important. You cheeky, saying I'm 40. But yeah, it'd be lovely if you guys could leave a review. And thank you, Rani, as well for your help. Thank you, all the mods. And guys, thank you for being so active in the chat. Like a lot of you were just like putting in questions there, constantly asking like extra physics stuff. And I really appreciate the lot of you who kept being like, physics, physics, physics. I know there were some people being a wee bit off, but we just ignored them. And I really think that you had a really productive 3 hours. Like it was mad. Not even 3 hours, 3 hours and 10 minutes. Fleming's left-hand rule is the motor effect, just on the chat. Fleming's left-hand rule is the motor effect. The grade boundaries, normally it's like 70% for an eye. But yeah, I hope you guys found it. I hope you like it. You got it for guys for free, which is mad. Nothing in life is ever free. Oh, you know that saying, it's too good to be true? Other than this one time, that has to still apply. There's loads of scams out there. So just in warning, if you're ever in Camden especially and something's too good to be true, it is fake. Especially in Camden. Do not go there. But yeah, have a lovely day. I hope you guys enjoyed it. And good luck. Good luck tomorrow. Have a good night's sleep. Make good choices. Cece, Bubba Juk. Where's Bubba Juk? Bubba, come on. Come here. I can show you them on my carpet. But yeah, he's a lazy git. Can you see him? Where is he? You see his tail. He's just like looking. He's like, I ain't moving. Bubba. Yeah, he's like, I ain't moving. He's done. He's just done. But guys, especially if you're on the main course this year, you guys smashed it. Like you actually progressed so much and should be so proud of yourselves. Like, I don't know anyone from the main course. So the main course, if you don't know about it, we did a course all year with GCSE kids. And just seeing you guys progress from what we did in the main course at the very start to now. And like, hopefully some of you like can see that, like Ayush and all, like hopefully somebody can see that, like now in this chat with everybody else, how much you guys have learned over the year. So some of you did amazing, right? So yes, CC, some of you did amazing, yeah. Tahima, yeah, like honestly, so good, so much progression. Yeah, we're doing A levels next year, and we've got a summer school. So if you want to do year 12 physics and year 13 physics, we have a full course. You can join us. But yeah, or see you in summer school. But don't worry about that right now. Just do tomorrow, right? Focus on tomorrow, and then tell us on TikTok how you did, right? Yeah, see you at A level, please. Is it free? No, it's not all free. No, it's not. We just did this for free to help you guys out. But yeah, don't worry about the course and all that course. We'll tell you all that stuff on TikTok and Instagram. Just you worry about right now about tomorrow, right? Just worry about tomorrow. Get a good night's sleep. Get that last minute revision in. If you haven't done that mock that I sent you for the Easter revision course, do it now, right? Guys, you're so welcome. See you later, guys. Have a lovely evening. Have a lovely evening. Bye, bye. Bye, guys. Good job today. Good job, good job, good job. Bye.